This is Software-Defined Networking with NSX, a PAC publishing video production authored by Yves Sanford and Matthias Eisner. My name is Yves Sanford. I'm the CEO of the ComDivision Group. I'm also VMware Certified Design Expert number 203, Certified Implementation Expert for Network Virtualization. I have a 7+ years VCI background, over 20 years in the IT industry, more than 20 years around in networking, and more than 10 years around the VMware space. My Twitter handle is @Yves Sanford if you want to reach out to me.
Hello from my side, my name is Matthias Eisner. Within the ComDivision Group, I'm the Director for Cloud and Management. I'm a VMware Certified Implementation Expert for Network Virtualization as well, and I'm working more than 7 years as a VCI. I have more than 15 years experience in IT and I'm working within the VMware space for more than 10 years right now. If you want to reach out, my Twitter handle is @Matthias Eisner. Let's take a short look at the roadmap within NSX. So we're talking about NSX and how to achieve the software-defined networking. And we're getting started with NSX, looking at the installation, doing some routing with dynamic and static protocols, and talking about the ESG and DLR. We're exploring the NSX edge services, especially load balancing and VPN. We're talking about firewalling, especially the distributed firewall and how the firewall is approached in the modern SDDC. Within NSX, we are always discussing the three options we have: the management, control, and data plane. So what we do in this training is we're checking the data plane. How is the relationship between the NSX manager and the vCenter server? How does the control plane components interact with each other? And how is the data plane involved in handling the whole traffic? Discussing vSphere side like the DVS, the distributed virtual switch, and the kernel modules which are all installed with NSX. We're also taking a look into the communication. How does the components interact or communicate with each other, especially the message bus agent and the user world agent?
Let's take a closer look into some of the demos we are going to provide. In this scenario, we are going to show how to deploy a controller. We are also in many cases going to take a closer look into console access, how to validate certain settings, and how to complete the setups, and give you some best practice advice on how to use them in a daily operation.
As discussed in the roadmap, we're taking a closer look to routing, and we're also going to cover why do we need dynamic routing within an infrastructure instead of just using static routing. And NSX enables to use dynamic routing protocols within the infrastructure to allow communication across the whole environment.
In a live demonstration, we are going to show you how to configure OSPF on an Edge Services Gateway as well as on a distributed logical router. We are also going to validate OSPF commands via the command line on an Edge Service Gateway as well as on distributed logical routers.
Back to the roadmap. Let's start to explore some edge services. In the training, we're discussing basic load balancing and how NSX deals with load balancing and enables a couple of users to access a pool of backend servers for availability and load balancing.
In another lab scenario, we are going to show you how to configure different VPN and load balancing scenarios. And we are going to show you live how SSL VPN can be used and set up between a standalone Windows box and an NSX environment.
Back to the roadmap again. So let's dig into firewalling with the NSX distributed firewall and ESG services. Within the training, we're covering the firewall approach NSX uses. So in the past, we had a physical firewall, we had all the virtual machines connected to the physical firewall. But within NSX, we use new features like DLR, and we're trying to add security into single subnets, and that allows us to distribute the firewall across the whole infrastructure, even onto each single virtual machine. One of the goals of this training is to keep everything together, because in the real world scenario, we don't have only virtual machines. So we have physical boxes or the physical space, we have the virtual space, and we discuss how perimeter firewalls are used within the infrastructure, or we use ESGs and the distributed firewall on top. So everything works together and physical servers still use the physical firewall box, but virtual machines and the whole traffic can be kept within the virtual space, and that was one of the main goals of NSX.
Finally, all the live demonstrations we have in this training are going to give you some best practice and real-life scenarios which you can easily adopt for your own environment and your own implementation. There are, however, some prerequisites when you take this live video training. So first of all, you should have some basic vSphere knowledge, you should have some basic networking knowledge, and you should have access to a vSphere environment, ideally something like a lab environment which you can break by intention. And finally, you will need access to the NSX binaries to be able to replicate some of the stuff we did in the training. You can just watch the videos, which is fine, but in the end, you want to actually play around with it yourself. And the more you are going to play around with it, the more you will start loving it. So get yourself ready and get some access to the NSX binaries from VMware.
Welcome to Software-Defined Networking with NSX. In the first section, we're going to cover the installation and setup of NSX. In this section, we're going to take a look at the NSX component overview and do a live demo of the NSX controller deployment and the ESXi host preparation. The first video in NSX covers the NSX component overview. In this video, we're going to take a look at the management, control, and data plane, the NSX manager, the NSX controller, and lastly, the ESXi host components. Let's start with the management, control, and data plane. We have two sections. We call them data and communication. So for the data in the management plane, we have the vCenter server and the NSX manager. These two always form a one-to-one relationship. That means that a vCenter server can have only one NSX manager attached, and one NSX manager can only be connected to one vCenter server. The control plane is responsible for configuring the whole infrastructure and make sure that you have a consistent configuration across the whole environment. Within the control plane, we have the NSX controller and the DLR control VM. So the NSX controller is responsible for ARP suppression and answering questions of the VTAPs. The DLR control VM is responsible for keeping a consistent routing configuration across all the ESXis. The NSX edges are kind of half control plane and half data plane because they own their own configuration and they have to make sure that they have a consistent configuration, but on the other side, they're responsible for handling data. That takes us straight into the data plane. Each component within the data plane is responsible for handling data or shipping traffic from A to B. So we have a vSphere component, which is the DVS, the distributed virtual switch, plus the ESXi kernel modules. They consist of the distributed firewall, the distributed logical router, and the VXLAN or VTAP kernel module. So these components are responsible for handling data. On the communication side, we have the message bus agent and the user vault agent. So they are both installed on the ESXi, but they reside in different planes because the MBA is part of the management plane because it's communication only, and the UWA is kind of a control plane even though it's a communication agent because it is responsible of receiving the rule sets from the NSX manager and configures the distributed firewall kernel module inside the ESXi. Let's start with the NSX manager in a more detailed way. The NSX manager provides the management UI. This is done by installing a plugin in the vSphere web client, and it provides the REST API for automation. It generates the certificates which are needed to secure the communication between the components within NSX. It deploys the NSX controller cluster, so the NSX manager VA virtual appliance consists or has the OVAs needed to install the cluster virtual machines. It installs the components to the hosts. This is done via VIP install. VIP is a VMware infrastructure bundle, and this is a standardized method of installing kernel modules into an ESXi. Lastly, it configures the communication agents being able to talk to the NSX manager on one hand and to the ESXis on the other hand.
How's the secure communication done? So we have our NSX manager, which provides, as we have already said, the UI and the REST API. REST API is just to be consistent across the whole product, and the REST API can be used by external tools to automate NSX. For example, vRealize Orchestrator. The NSX manager generates the certificates, and they are stored in the database, which is local within the NSX manager virtual appliance. After the certificates are generated, the NSX manager is used to deploy the NSX controller cluster. This is done via an OVA deployment. After they have been deployed, the NSX manager is used to install all the components on the host. So again, we have the 3 kernel modules, the DFW, the DLR, and the VXLAN, and the 2 communication agents, the NetCPA and the UWA. After the installation is done, the NSX manager uses an API call to the NSX controller, and the NSX controller switches to a SSL over HTTPS communication, and therefore using the self-signed certificates. So these certificates can't be exchanged, and it's not necessary to change them because it is infrastructure internal communication only. Let's take a look at the NSX controller cluster and what are the responsibilities of this system. Firstly, we have the VXLAN and routing information distribution. So the NSX controller cluster updates the VTAPs and updates using the NetCPA, the DLRs on the hosts, that they have a consistent configuration. The NSX controller cluster uses something we call a scale-out configuration. So we use multiple instances for performance and, more important, for availability. It is used for our broadcast traffic suppression. We'll take a closer look into this one a little bit later. And it maintains tables for VTAP, MAC, and ARP. And these tables are used to answer questions from the VTAPs if they might need which virtual machine is behind which VTAP, or do you have the MAC address of a specific virtual machine. Let's do NSX controller availability. All the objects we have within NSX, the logical switches, or short, the VNIs, or the logical routers. So all these objects are sliced. That means each object, or the information per object, is divided into multiple pieces. And these slices are stored across the NSX controller cluster nodes. As you see, we display only 3 nodes because this is the only supported amount of NSX controller nodes for NSX for vSphere. For each role, so we have 2 roles over here, the VXLAN role and the router role. For each role, one of the 3 controller nodes is the master. The master is responsible for having a consistent configuration across the different nodes. As we have mentioned, we use a scale-out configuration for availability. So if we lose a node, it doesn't matter because the 2 remaining nodes have enough information or enough slices per role to recreate the whole information. HA on the other side takes care of restarting the failed node on a different ESXi, and that node joins the cluster again and the whole information is redistributed. The NSX controller tables. We have 3 tables. The first one is the VTAP table. This table contains a mapping between a VNI and a VTAP IP. So each VTAP having a VNI configured has an entry within the table and the NSX controller cluster. And the NSX controller cluster distributes this piece of information proactively to each VTAP within NSX. Second table is the MAC table. This contains a mapping between the VNI, the MAC address of the virtual machine, and the VTAP, which is responsible for a virtual machine. So this table is used if a VTAP talks to the NSX controller cluster asking, could you please provide the VTAP IP for a specific virtual machine MAC address within a VNI? The NSX controller is able to answer that one. And the last table is the IP table. This one contains the mapping between the VNI, the IP address of the virtual machine, and the MAC address of the virtual machine. This one is used to suppress ARP broadcast traffic because the NSX controller is able to answer an ARP request in behalf of the VTAP, or be more precisely in behalf of the destination virtual machine. Let's do the ESXi host components. Firstly, we have the VXLAN kernel module. This one is installed and is responsible for being the VTAP and doing the VXLAN traffic encapsulation and decapsulation. Basically, this kernel module configures a VM kernel port on the host, assigning the IP address drawn from the either VTAP IP pool or DHCP assignment, depends either or, but basically it uses a VM kernel port. The second one is the distributed firewall. This kernel module instances itself on a per VNIC base. So that's a virtual network interface card per virtual machine. So we have one instance per VNIC. Important thing to mention over here is the distributed firewall works independently of the VXLAN. So there is no need to have an overlay network or anything else in place to use the distributed firewall. So this is the only feature which can, within NSX, which can be used kind of standalone. Last but not least, we have the DLR. The distributed logical router is responsible for doing the routing local within the host, not having the traffic traveling to an external physical router. This one, or we can have up to 1,000 DLRs per host, each having 1,200 interfaces. So these kernel modules are installed as VIPs, as VMware infrastructure bundles, and this is a standardized way to install a kernel module into an ESXi. The last piece we'd like to cover over here is a construct we call a transport zone. So the transport zone defines on which hosts a logical switch is created. That might be interesting if we have licensing or we have a cluster per software or per application. So transport zone makes perfectly sense just to make sure that a VNI might not exist on a host. So we do a short example. We have 4 ESXis, and what we could do is we call that a global transport zone. So a transport zone spanning all hosts of our infrastructure. If you create a new VNI or a new logical switch, you're able to select in which transport zone this switch is going to be created. If you choose the global transport zone, the VNI will be available on each of the 4 hosts, thus allowing you to vMotion a virtual machine between all of these hosts. What's pretty cool in NSX, an ESXi can be member of more than one transport zone. So we could create a second transport zone, we call it left transport zone, and only the 2 hosts on the left-hand side are a member of this transport zone. If we create a new VNI and select the left transport zone, this VNI is only available on the 2 hosts on the left-hand side. That's how you use transport zones to segment your infrastructure further. The next video will be a live demonstration about the deployment of the NSX controller cluster.
In this short video demonstration, we are going to show you how to roll out the NSX controllers in a vSphere environment. This is going to be a live demonstration. Before we start into the live demonstration, let's take a closer look at the demo scenario we created. In this demo scenario, we actually have 2 different networks. One is called the management network, which is 172.17.10.0/24, containing a set of virtual machines. So we start with the vCenter server appliance and NSX manager and 6 ESXi hosts, 3 for management and 3 for resource purposes. This network is also going to be used for VXLAN transport as well. In a real-life practice example, you would normally actually have a dedicated network for VXLAN transport, but to keep the lab environment rather simple, we actually combined the two. We also have a production network involved in this specific demo scenario, which is going to be sitting on the IP range 172.17.20.0/24, so it's also a Class C network. For this specific demo scenario, we are going to deploy what we call the NSX controller cluster, consisting out of three different VMs, and they will get the IP addresses 172.17.10.43 to 45. We are going to continue to work with the demo scenario slides in the upcoming labs as we are going to build up different scenarios, so you can always come back to them and see what exactly we built in this specific lab scenario or live demo scenario. We are going to deploy the controller next. First, we are going to log into the vSphere web client. For this, I'm going to use the administrator at vSphere.local account with the appropriate password. For sure, you can later on create your own user accounts if it becomes necessary. Once we are logged into the vSphere web client, we are going to click onto Networking and Security to enter the NSX configuration area. We are going to switch to the installation area. For that, select Installation from the left-hand menu. Within the installation area, we are going to start with the control cluster first. For this, we are going to deploy 3 different controller nodes, one by one. Always deploy the controllers one by one. Start with the first one, wait for it to be completely finished and in sync, then the second, then the third. If you are going to roll out the controllers in parallel, you risk that they become completely unusable and that you have to reinstall everything. Let's start with the first one, which is actually requiring a few more configuration parameters than the other ones later on. So first of all, you pick the NSX manager, then the data center, and if you want to cluster resource pool, so you pick just at least your cluster. Then you pick the data store. This should be a shared data store for sure. Next, decide whether you want to put it into a folder or whatever. We have pre-created an NSX controller cluster folder. Next, select the available object, in our case the distributed switch port group we are going to use, and then you need to create a new IP pool for this. IP pools are used to store combined information about the IP network, the available IP addresses in the segment, DNS servers, and other informations. IP pools can be used in NSX for controller deployments as well as for VTAPs. You normally use them to provide IP information when you are not using any kind of automatic deployment like a DHCP server. We are going to call the IP pool for this NSX controller. You will later on create another IP pool for the VTAPs. Provide at least the gateway IP address, in our case 172.17.10.1, a prefix length. DNS information is purely optional, and then finally you need to provide the information for the static IP pool. We need 3 IP addresses as we are going to roll out 3 controllers. If your VTAPs would be later on in the same IP range, you could use the same IP pool. However, I typically prefer to have a specific IP pool just for my NSX controllers. Select the pool and provide a password. Be careful here, let me quickly show you what happens if you use a normal 8 characters password. You need to have at least 12 characters, uppercase, lowercase, special characters, and some numbers in there. The 12 characters are typically the biggest issue, so provide a long enough password for the NSX controllers. You need to do this only for the first controller. All 3 controllers will always get the same password information for the rollout. The deployment typically takes between a couple of minutes to 15-20 minutes, depending on your storage performance, etc. If, however, it would ever take longer than 30 minutes, you would have a serious problem, because then the controller deployment will be reversed. Our first controller is now deployed. Let's take a quick look at the console window and log into the remote console of the NSX controller. In our case, what we want to quickly check is if the controller joined the environment completely, if all the settings are working. For this, we are going to log in with user admin and the password we used before, and then we are going to run a show command. You can always run show question mark. In our case, we are going to take a look at show control cluster status, and this tells us that we joined completely the control cluster, even though we only have one node so far, and that all the configuration is active and has been basically configured. Let's now deploy the other two controllers with the same procedure. Again, hit the plus sign, define the data center, the cluster, any additional information like the data store, folder connected to, again, is the distributed switch port group we are going to use, and pick the IP pool we used before. You do not need to re-enter the password because that's set for all controllers being exactly the same. The controller deployment by itself, once the first node and second node are in sync. Let's add a third controller next, now that we have two controllers, and then we are basically prepared from that perspective and can move on to the host preparation in the next segment. Same procedure, distributed port group, IP pool, hit OK, wait for the controller to be deployed. Again, takes a couple of minutes, and then we should have our third controller deployed into the environment as well. In our next video, we are going to show you how to do the ESXi host preparation. Next, we are going to do the ESXi host preparation. In this video, we are going to take a closer look at how to install VIBs on the ESXi host. VIB is short for vSphere Installable Bundle. It contains necessary modules which we need on the ESXi host for features like distributed router, distributed firewall, or the basic VXLAN functionalities. Then we are going to take a look at the segment ID pools, and finally we are going to create a transport zone. This is going to be a live demonstration. In this demo scenario, we are going to prepare the hosts with specific modules, so they need to be installed on the specific hosts. In the previous demo, we already created the NSX controller cluster on the left-hand side of the demo scenario. What we are going to do next is use the NSX manager to install the individual kernel modules onto all 6 ESXi hosts. For the network hypervisor NSX to work in our ESX environment or vSphere environment, we need to prepare the hosts also. So beside deploying the NSX controllers, we need to prepare the hosts. Pick each cluster, hit Actions, Install will prepare the hosts with the necessary VIPs. These VIPs are going to provide functionality for the distributed firewall, logical router, VXLAN, but also the user vault agent, or short UWA, and NetCPA. All of the installation is being operated by the NSX manager and prepares the ESXi host also with the certificates so that later on the communication from the NSX controllers can be done directly with the hosts in a secure and encrypted fashion. Once all of the hosts are prepared, you will see that the installation status shows you always the version number of NSX being deployed on the hosts, and the firewall checkmark tells you that the distributed firewall features are enrolled on each host. The next step is to configure VXLAN with a new IP pool and to choose also the teaming methodologies for it. For VXLAN to work, you need to specify the switch, which should be a distributed switch, VLAN, MTU size, and you can also specify the teaming policy. We are going to stick with failover in this case. I personally prefer to use an IP pool because that way I have more control about the IP range being used. You could also use DHCP. I'm going to name the pool in this case VTAP pool because all my VTAPs are going to be in the same network. If I were to use, for example, a multi-rack scenario or something else where I want to have specific different IP ranges, I would actually split the different pools for that specific use case. But in this case, we are going to just create the VTAP pool. Again, this pool needs to get a name. We are going to define the default gateway for it, the prefix length, And we always tend to define the DNS and DNS suffix in our environments, but this is optionally. As you can see, there is no red star beside it. The static IP pool defines the IP range which can be used. In our case, we only have 6 hosts, and as we picked failover, we will only have 1 VTAP per host, so a range of 10 IP addresses should be good enough. We hit OK, the IP pool is created, automatically selected, and we can then click OK. And now the resource cluster will now be configured for VXLAN usage. Same applies to the management cluster. We hit not configured, same settings. Basically, the only thing we can pick now is the VTAP pool. Everything else we leave the same as before. Again, the preparation of the individual VXLAN components is a rather straightforward and quick process. It typically takes a couple of seconds because the VTAP, the VM kernel ports, are being created on the individual hosts. What else could we do from here? We could actually change the IP detection type. This is actually being useful if we are going to use specific VTAP scenarios. But in our case, we can just leave that as is. Logical network preparation, that's our next step. So we need now to define or validate that the VXLAN transport has been set up. And then we can specify the so-called segment ID. This is rather similar to your VLAN ID. So we are going to pick the range from 5000 to 9999, which will actually give us 5000 VXLAN IDs. It's a VMware specific that we are not going to use any VXLAN ID below 5000 just to actually keep them strictly separated from VLAN. Finally, we need to define a transport zone. A transport zone always needs to span a complete distributed switch or multiple distributed switches. And this is basically the area or IP area where the VXLAN can actually span the network environment. So in our case, we are going to call this after the data center name. So our data center is called HQ-DC. And once the transport zone is created, we are ready to set up our first logical switches. Now that we have deployed all the necessary bits and pieces for our NSX VXLAN environment, we want to take a few more minutes to discuss the packet flow of a simple VM to VM communication, starting with an ARP request and how a feature called app traffic suppression is going to be used in NSX environments running in unicast or hybrid replication mode. Let's first set the scene for this. So in this scenario, we have 2 ESXi hosts, ESXi 01 and 02 represented by the gray boxes, and you have 2 networks involved, the management network, the orange one at the top, and the violet VXLAN transport network at the bottom. You also see here that we have 2 VM kernel ports per host. One for management, one for VXLAN communication, which is called the VTAP for VXLAN tunnel endpoint. We also have 2 VMs involved here, VM1 and VM2 sitting on 2 individual hosts. Both of them are connected to the same VXLAN VNI 5001 in our scenario. In theory, it doesn't matter whether these ESXi hosts are in the same IP network or in different networks. The only important piece is both of the ESXi hosts can reach the NSX controller cluster and are linked to the same VXLAN transport network. Let's take a closer look on how the 2 VMs communicate with each other. Before 2 VMs can communicate over their IP addresses, which in the end leads to traffic communication over the MAC addresses, VM1 needs to know what is the MAC address of VM2. So this is normally done by sending out an ARP who has request to the broadcast network. This is still going to happen the same way, so there is no IP change or network stack change within the VM. So the VM by itself sends out a normal ARP who has request to the destination MAC address FFF, which is actually representing broadcast, so being sent out to all machines. This frame is actually going to go onto the VXLAN and the VTAP is going to pick this one up. The VTAP actually, instead of sending out a broadcast now, is going to take a closer look at it and figure out, okay, this is an app who has requests. I can actually answer that in many cases. So what the VTAP is going to do next is actually leverage the management network to talk to the NSX controller cluster and forward the app who has requests to the NSX controllers. They should know the MAC address of VM2 and will actually provide the information back to the ESXi host 01. So we will now actually see the app request being responded by the NSX controller via the VTAP to the VM1. So again, important piece here, no changes within VM1. The machine actually sends out a normal app who has request, but it's not going to be broadcasted to the overall network. It's going to just be responded by that VM1. This is going to reduce the traffic and load on your overall VM environment quite a bit. Now that VM1 actually knows what the MAC address of VM2 is, we can actually establish our direct unicast communication from VM1 to VM2. However, we have a VXLAN involved, so there is a bit more which is going to happen next. So VM1 is going to send out the packet to VM2, and it now can actually use the MAC addresses for the traffic communication. So that packet is going to be picked up by the VXLAN tunnel endpoint, or VTAP, and that is actually going to encapsulate this payload information into the overall VXLAN communication. So we will now have a VXLAN packet going from VTAP1 to VTAP2, including the payload of the original layer 2 frame from VM1 to VM2. This unicast frame is going to be moved to the other VTAP next, who is going to, on his side, actually decapsulate the frame. So the payload information is released back onto the VNI 5001 and will finally reach VM2. This is all which is going to be to it from a VXLAN unicast traffic communication perspective. It's actually for you only important that all the encapsulation, decapsulation runs in the backend. All you need to set up is the logical switches, the VNIs, and the VTAPs for it. In our next video, we are going to take a closer look into the logical switch creation. This video is going to cover the creation and use of logical switches. We are going to live demonstrate to you how to create a logical switch with NSX and vSphere, and then how to attach a VM to the logical switch. In this demo scenario, we are going to create logical switches. For this, we have pre-created 4 VMs displayed at the lower right corner of this screen. We have 4 VMs, 2 web servers, web server 01 and 02, both in the same network. We have an app server and a DB server, both in each one of them in a separate network. These individual VMs will actually be connected over logical switches. For this, we are going to create a web tier logical switch for the web tier network 172.30.11.0/24. One logical switch for the app tier on 172.30.13.0/24. One for the database tier, which is going to be 172.30.12.0/24. And then finally, we are pre-creating a transit network on 172.30.1.0/28. So far, we only created logical switches. There is going to be no routing whatsoever between these individual VMs. This is going to be added at a later demo scenario. We are going to create now 4 logical switches. 3 are going to be linked to VMs, and 1 is going to be later on used as a transit network for north, south, east, west routing. To be able to create a logical switch, we need to go into the NSX configuration, which is network and security. Then there is logical switches in the left-hand menu. And within that, you can just actually create a new logical switch. Our first one is going to be called web tier. We are going to define which transport zones the switch is going to be linked to, and the replication mode. In our case, we are going to use unicast. We can also enable IP discovery and MAC learning. We are going to keep the defaults for now. We are going to create a few more switches now with similar settings. So this is going to be the DB tier, the app tier, and finally transit network. As you can see also, the NSX has automatically applied segment ITs to the logical switches. Before we are going to take a look into how this is represented in our distributed switch, let's attach some virtual machines to the individual tiers. The VMs we are going to use for these demonstrations are just straightforward Linux VMs, but you could actually use whatever suits you. So I'm going to hit the Add VM feature here, and I'm going to select Web Server 01 and Web Server 02. You then can pick which NIC you want to actually link, and that's all you need to do. Now the two VMs are linked to our web tier. We are going to do the similar action for our DB tier and our app tier. So for the DB tier, the DB server is going to be linked. Again, select the network adapter, and the same applies to our app tier. So far, we have not yet set up any routing or anything else, so there will be only communication within the VMs on one application layer and not cross the individual tiers. This now has actually given us the ability to link the different VMs. I'm now going to actually open the console of one of the VMs, which is Web Server v01. So I search for it, and now I get all the information about the individual machine. I can actually take a look at the VM hardware. And you can see here that it is actually connected to a specific distributed port group, which also has the VXLAN ID 5000 and the web tier name in it. I'm going to open a console now to ping from one host to the other one. This is going to be a straightforward demo. We don't want to actually make it too complicated. I'm going to ping 172.30.11.12, which is the other VM in the environment. This concludes the first section of this NSX training video. We discussed the NSX components from management over control to data plane, the use case of the NSX manager, the NSX controller deployment, that you have 3 of them, the ESXi host preparation, which is going to deploy the VIPs onto the host, and also how to set up the basic VTAP environment for your VXLANs. And finally, we created our first VXLAN or logical switch, how we used to call them in an NSX environment. In the next section, we are going to discuss static and dynamic routing.
In section 2, we're going to cover static and dynamic routing. In this section, we're going to take a look at dynamic versus static routing, dynamic routing OSPF, dynamic routing BGP, and routing architecture. The first video will cover the difference between dynamic and static routing. In this video, we're going to take a look at a brief routing recap and why we need dynamic routing. So let's start with a short switching recap. I assume that the two servers have already done an ARP broadcast to recognize the MAC address of the other system. So in switching, we have two systems, an Ethernet switch, and if server 1 wants to talk to server 2 and he has already done a broadcast, he knows the MAC address of the second machine, thus allowing to send the Ethernet frame directly. Because of the IP address, server 1 knows he is able to talk to server 2. So what happens is the Ethernet frame is sent via the physical NIC to the switch. The switch performs a switching table lookup, recognizing the MAC address is connected to a very specific port, and delivers the frame to the second machine. So switching is a pretty easy and straightforward process. Let's continue with a brief routing recap. In this scenario, we have again two servers, but they are residing in different IP subnets. IP subnet 1 has the IP address range of 192.168.10.0/24, and IP subnet 2 has 192.168.20.0/24. Each of the servers have an IP address configured from that specific subnet, and they have a default gateway. The default gateway is an IP address or an interface of a physical router configured in that specific subnet. So basically, on the physical router, you add an interface, you attach it to a network, and you configure the IP address. If server 1 wants to talk to server 2, it is possible. This is possible because a router always learns from local connected interfaces, because each interface has an IP address and a subnet mask. As soon as you configure an interface on a router, the router creates an entry in the router table saying, on interface 1, I have the IP subnet 192.168.10.1 because it's its own IP address /24. Basically, you can use every IP address from the subnet, but in most cases you use either 1 or 254 in the last octet. So the second interface is configured in the second subnet, but it's exactly the same. It's a local interface to the router, so it creates a second routing table entry. If server 1 wants to talk to server 2, what is going to happen from a layer 3 perspective, because routing is layer 3? The OS of server 1 compares the IP address of server 2 with its own IP address and the subnet mask, leading to the decision that server 1 is not able to talk directly to server 2. So the decision is, I need to send the Ethernet frame to the default gateway. So it's just doing an up broadcast, who has MAC address for IP address of the default gateway, and so on and so forth. It's exactly the same, but the Ethernet frame is sent to the router, and the payload of the Ethernet frame is the IP packet. So the frame contains the IP packet, which contains the source and destination IP address, and the payload is the layer 4 datagram. So what happens now is server 1 sends the Ethernet frame to the router. The router grabs the frame and extracts the payload, looks up the destination IP address. So the next step is the router has to make a routing decision. In our case, he makes a router table lookup and discovering that the destination IP address is local to this specific router. So the router uses its own MAC address and substitutes the source MAC address with its own, because the reverse path of the traffic needs to go via the router as well, and delivers the frame to the destination machine. So that's a very basic routing recap, having a router with only local subnets and local interfaces. So there is no need to do any additional configuration on this machine. But what happens if we have a more complex scenario, and why would we need dynamic routing in our infrastructure? So the scenario we have contains 3 routers: the backbone router, router side 1, and router side 2. Each site routers have 2 direct attached IP subnets with configured interfaces, and we have 2 additional transit subnets to allow the routers talking to each other. As we have already spoken, if we have two machines sitting in subnets which are local to a specific router, there is no need to do any additional configuration except of configuring the interfaces. The router at site 1 creates router table entries for these two subnets, thus being able to route between those two. So virtual machine 1 and virtual machine 2 are able to talk to each other, even though they are sitting in different IP subnets. As we've mentioned, it learns from connected networks. A complete different story. If virtual machine 2 would like to talk to virtual machine 3, it is not possible. So VM2 sends the Ethernet frame to its local gateway or default gateway, which is the router at site 1. And the router at site 1 does a router table lookup, finding out he has no clue about the destination IP net. So what it does is, because it has also a configured default gateway, it sends the Ethernet frame to the backbone router via the transit subnet. And the backbone router does a router table lookup and not having any entry. So it is not able to route to the destination network. So how can we solve that problem? The easiest solution would be we just configure the static routing. So we just go to the router and configure the routing table, just creating entries. So you can reach IP subnet 1 via interface 1, you can reach IP subnet 2 via interface 1, and so on and so forth. But that table is created and maintained manually. So that's lots of administrative overhead. But after implementing the static routing, virtual machine 2 and virtual machine 3 are able to talk to each other because the backbone router has the knowledge about all the subnets within our infrastructure. So that's lots of administrative overhead, and that leads us to why do we need dynamic routing? It would be very cool if the router at site 1 and the router at site 2 could tell the backbone router, hey man, I got a new IP subnet, and this is the IP subnet, and it could be reached using me. So that saves a lot of work and reduces administrative overhead a lot and leads us to highly automated virtualized networks because you can't configure everything manually. The next video will talk about dynamic routing using OSPF. Welcome to this video within Software-Defined Networking with NSX, talking about dynamic routing with OSPF. In this video, we're going to take a look at dynamic routing using OSPF and how does OSPF basically work. What is OSPF? Firstly, OSPF is a dynamic routing protocol. That means that different routers are able to exchange routing table information with each other. The acronym stands for Open Shortest Path First. That means how OSPF decides which, if there are more than one path, which path is going to be used to transmit the information. OSPF operates within an autonomous system. So OSPF is considered as an interior gateway protocol. To connect different ASs together, you mainly use BGP, which is going to be covered in the next video. OSPF is for routing the internet protocol only. OSPF uses a functionality called areas. Areas are used to combine different routers and configure which routers are going to exchange information. And therefore, we have different types of routers. We have backbones, AABRs, ASBRs, and they are going to be covered within the next slides. So firstly, how does OSPF calculate a route? In our example, we have 4 routers connected with different link speeds to each other. In this example, I refer to the northern route and the southern route. In the northern area, we have 3 1 gigabit links, and in the southern area, we have a 100 megabit link. And OSPF uses something called cost. There are default values, but they can be configured as well. In my example, I'm using a cost of 20 for the 100 megabits and a cost of 3 for the 1 gigabit interfaces. That means less bandwidth costs more. So if everything is up and running, the router just does a simple cost calculation. It says, if I go from the left to the right side, the 100 megabit connection has a cost of 20, or if I use the northern route with the gigabit interfaces, I have 3 times 1 gigabit, and that leads us to a total cost of 9. So if everything is up and running, the left router, if we are going to talk to a destination network, always uses the northern route. And that's exactly what's going to happen. If we have an IP packet traveling from our source network to the destination network, it is sent to the router, the default gateway, and it takes the northern route because it has less cost. If something happens in the northern route, we lose a connection between two routers. So the involved routers are reforming their adjacencies. The router on the left knows I can't use the northern route anymore because a path is broken, and therefore we have only one link left, and that's the 100 megabit link. So if something happens within the mesh of the routers, they recalculate their adjacencies and are able to use a different route to transmit the packet. Let's talk about areas. Within OSPF, areas are used to create smaller, manageable pieces of the infrastructure. Each area contains routers. Within OSPF, we always have the backbone area, and the ID of the backbone is 0. So it's pretty simple. If you have a router with a couple of interfaces in the backbone, just add the area ID 0 to each interface, and that makes this router a backbone router. We can configure an additional area. So we have an internal router in the middle of the blue bubble with 3 interfaces, and these interfaces all have the area ID 10 in our example. On top of that, we configure something we call an ABR, an area border router. This router is a special type of OSPF router because in our example it has 2 interfaces, but one interface is associated with the area ID 0, that's the backbone, and the other interface is associated with the area 10. Now, these 3 routers start to exchange hello packets, thus leading to allow these devices to form adjacencies and talk to each other, and they start immediately exchanging routing information. We can add another area with ID 20. We need another ABR. We have an internal router with a couple of interfaces. They're all configured with area ID 20, so we can have multiple areas. Within OSPF, each area is connected to the backbone. There is a third router type I would like to mention over here, and that one is called an ASBR, an autonomous system border router. These routers are used to connect external information to, or external ASs to our infrastructure. So there's a different AS, it has an ASBR as well, and these two might talk BGP in most cases, but we can connect to different ASs as well. How does the routing information exchange work? I created another example. So we have again a backbone router, we have 2 ABRs, one on the left, one on the right, we have 2 internal routers, and as you can see, they have only one interface with a subnet connecting to the ABR, and the ABRs have different subnets connecting to the backbone router. So they have already exchanged the hello packets, and these routers are all already exchanging routing information with each other. When using OSPF, each router has a routing table as well. So, as I've mentioned, they have already exchanged routing information. So the internal router in area 28 has a routing table which may look like this. So it knows the 4 subnets and the interface, how these subnets can be reached. So in this case, it's always interface 0 because the router has only one interface right now. We can now configure a new interface on the router. So in our example, it's interface 1. The interface gets the same area code like the other interface, because that router is an internal router. So we have the area ID of 28, and the subnet in our case is 10.120/24. So that's the new IP subnet. Because of the interface configuration, because it's a local interface to the router updates its table. So that's basically routing, or that's what a router does. It just updates the local table in the first place. After updating the local table saying interface 1 has the network 10.120/24, this piece of information is going to be sent to the other routers. So if we use the ABR on the top left corner of the slide, this is the routing table of the ABR. So as we can see, there are a couple of networks and how they can reach using which interface. The internal router now sends an update information to the ABR, and thus leading the ABR to updating its routing table, adding the new created network 10.120/24. It knows I can reach this one using my interface 1. And that's how the routing information exchange works. And it goes so on and so forth. So the ABR sends the information to the backbone to the next ABR, and the ABR sends that piece of information to the other internal router. In the end, the internal router on the right hand side within area 51 knows exactly how to reach the network 10.120.0/24. That's a dynamic routing protocol, and it's really useful. If we create a new subnet in area 51 using a complete different IP subnet, the same process starts again, just exactly the other way around. And that's how it works. So a dynamic routing protocol helps a lot automating network provisioning from a routing perspective, allowing communication within our infrastructure. The next video is going to talk about dynamic routing with BGP. Welcome to this video talking about dynamic routing with BGP. In this video, we're going to take a look at dynamic routing using BGP and how does BGP routing work. A brief overview of BGP because it's kind of comparable to OSPF. BGP as an acronym stands for Border Gateway Protocol. So typically OSPF takes care of routing within an AS, and BGP manages the routing between different ASs, most cases. So the Border Gateway Protocol. The route information exchange works only with BGP peers. So you need to know which peer you can use and which router you can peer to. Otherwise, you can't establish any routing. So BGP is a dynamic routing protocol, but it needs lots of configuration up front. In BGP, you always need authentication. You can use authentication within OSPF, but it's kind of optional. Within BGP, you need to know the passphrase to access your peer. On top of that, BGP router administrators are able to configure which information is going to be exchanged with which peer. BGP has many different path calculation algorithms, and we're not going to cover these because it would be way too much stuff. So let's talk about BGP ASs. Each AS, autonomous system, has a number. So I figured out a couple of different numbers. In the real life, you cannot just use any number. These numbers are assigned by the IANA saying, okay, this is your AS number. If you have routers with many interfaces and you configure the same AS number for each interface, this router is considered as an internal-only router. If you have a router with interfaces and different configured AS numbers, they are border routers. Within BGP, we have two different protocols from a meaning perspective. So basically, they are exactly the same, but eBGP is used to exchange information between autonomous systems, and iBGP, on the other hand, is used to exchange routing information within an autonomous system. But in the end, BGP works within an AS, more or less comparable to OSPF. So we're not cover more about BGP at this point because it's an NSX training and not a networking routing training. So the next video is going to talk about the routing architecture within NSX. Welcome to this video within Software-Defined Networking with NSX, talking about the routing architecture in NSX. In this video, we're going to take a look at north-south routing compared to east-west and what that basically means within NSX. And then we're going to talk about when do we use edges or DLRs, or are we going to use these two together? So let's start with north-south routing. Basically, we have a virtual space somewhere in infrastructure, and I call that a physical space. So the virtual space contains all the virtual machines, and the physical space contains physical servers, or every infrastructure has something like that called a desktop or a client. Even though if you have all your server workloads virtualized, you still have physical clients accessing these services like file mail or anything else. So you need a mechanism to route the traffic between these two spaces. So in NSX, we call the north-south routing the path traffic is entering and leaving the virtual space. So north-south routing is mostly done using an NSX edge. So the NSX edge is kind of the interface or the device which routes the traffic between the virtual space and the physical space and or the internet. As we can see, the physical space and the internet connection, they are connected to a central physical router, probably including firewall capabilities, and the NSX edge connects to that physical box and providing the path for all the virtual machines. The NSX edge provides additional services like firewalling, load balancing, routing, of course, and VPN. So you can choose which services are going to be configured and enabled on the edge device. On the other hand, we have east-west routing. Within NSX, east-west routing is defined having traffic flowing between virtual machines. So we have a couple of virtual machines within the virtual space, and they are sitting in different IP subnets. And we need to enable the traffic flow from the virtual machines to others sitting in different IP subnets. So we call that east-west routing. So summarizing, north-south traffic from the virtual space to the physical world, east-west traffic being routed within the virtual space only. If we talk about the virtual space, we have something we call hairpinning. So let's do a brief overview. We have two racks or ESXis with different virtual machines, and we have a physical router. And these virtual machines are sitting in different IP subnets. So if they want to talk to each other, they need to use the router. So they send the traffic to the physical box because it's the default gateway for the OS and the TCP/IP stack. So if these virtual machines want to talk to each other, the traffic needs to travel the physical router. So that's not really hairpinning. So the hairpinning itself happens if virtual machines on the same ESXi having different subnets configured want to talk to each other, because the traffic flows from the virtual machine up to the physical router and back to the virtual machine, we might be running on the same host. So within NSX, we have a feature allowing us to provide hairpinning. Let's take a more detailed view on hairpinning. We have two racks of servers. We have top of the rack switches. We have distribution switches, and the core layer with a router. So they are all connected to each other using a full mesh. And we have a couple of virtual machines. That's kind of a logical view into the detailed hairpinning. Short recap. The virtual machine to virtual machine traffic in our definition is east-west. What happens if we have two virtual machines on the left-hand side want to talk to each other? So this is the logical traffic flow. We have two virtual machines sitting in different IP subnets, and the virtual machine just sends the traffic to the default gateway, and the default gateway takes care of routing the packet to the destination. So that's the logical traffic flow, pretty easy from my perspective. Let's take a look at the physical traffic flow. That's more interesting. I just came up with some flow in the physical network. I don't know exactly which path is going to be used, but the decision is done by the physical network. So the virtual machine sends the packet to the router. So it flows to the top of the rack, the distribution layer switch, to the core router. The core router does the routing decision and sends the packet back to the virtual machine. So as we can see, there are lots of devices involved within that very simple traffic flow from one virtual machine to another one. And probably these two VMs are sitting on the same ESXi. Within NSX, we have something called a DLR. That's a distributed logical router. So instead of using the central physical router for the east-west traffic, we could use the DLR. So the virtual machines are not using the central router anymore, and instead of that, they're using the DLR. As we have mentioned in the first module, the DLR is a kernel module, so it's installed on each host. So if we configure an interface on the DLR, because the routing configuration is done exactly the same as you would do a physical router configuration, you just access the DLR, connect it to a port group, and create a new interface and configure an IP address. And these interfaces are called a VXLAN live. So if you configure an interface like this, it is available on each host with the exact same MAC and IP address. But that doesn't matter because this interface is virtualized from the physical network using the VTAP. So the interface is sitting on each host. On top of that, we have the DLR control VM. This virtual appliance is very important because if you talk about a distributed configuration, you need to have a single management instance. From an HA perspective, the DLR control VM can be deployed in HA mode, which means you have two DLR control VMs up and running within an HA cluster. Let's talk about the DLR logical view. We have the DLR at the bottom with 3 networks attached to it, plus the DLR control VM. We have an NSX edge and a physical router. The DLR has, and that is different compared to physical router, 2 addresses. First, the forwarding address. This one is used for the data path, and we have the protocol address. As you remember, the forwarding address sits on each single host. That's a VXLAN live, but it's virtualized using the VTAP, or it can't be seen by the physical network. And the edge is not able to peer with a distributed system. That's what we have the DLR control VM for. And the DLR control VM has a protocol address, and that VM exists only once. So the DLR control VM is used by the edge for the routing peering, like a dynamic routing protocol, like OSPF, for example. And the edge on its own in the north-south route peers against the physical router. So the edge exchanges the routing information with the DLR control VM, and the DLR control VM is responsible of passing that piece of information by pushing routing table updates to each of the kernel modules. On the other hand, the forwarding address is used with the data path between the edge and the DLR. Let's talk a little bit about when are we going to use an edge and when are we going to use a DLR. So basically, north-south routing is done using an edge. East-west routing is done using a DLR. So that's a pretty straightforward approach. We have to keep in mind that the edge has additional services: firewalling, load balancing, and VPNing. I'm only mentioning these three services as side routing. So you could enable these services on the north-south edge, but you could also deploy edges into different networks and enable just a subset of these features like load balancing, VPNing, firewalling. You also have the possibility to deploy an edge behind an edge behind an edge. Always keep in mind, we can use more than one edge within our infrastructure. We have covered dynamic and static routing. We covered OSPF and BGP, both dynamic routing. And in the last video, we covered the routing architecture. The next section is going to showcase and demo the deployment of NSX routing with Edge and DLR.
In the next few minutes, we are going to talk about the deployment of NSX routing with NSX Edge and distributed logical router. In this section, we are going to look at the deployment of NSX DLRs for east-west routing and the deployment of an NSX Edge for north-south routing. We are also going to combine the NSX Edge and DLR for dynamic routing with the help of OSPF. In this first video, we are going to discuss the deployment of the NSX DLR for east-west routing. In this video, we are going to take a look at the deployment of the NSX distributed logical router and the setup of some basic routing. To deploy a logical distributed router, we are going to click NSX Edges, click the plus icon, and then a new wizard will open where you can choose whether you are going to deploy an ESG or Edge Services Gateway or a logical distributed router. In our case, we are going to start with a distributed router and we are going to call it the East-West DLR. We also can choose whether we deploy an Edge appliance for it, which is required for certain functionalities. We need to provide a username just in case we want to use the console access to the distributed logical router. So again, same password rules apply, and you can check whether you want to enable SSH access or just console access. Next, we have to decide whether DLR control VM needs to be deployed. We can pick either a resource pool or a cluster. We are going to deploy it on the management cluster, deploy it on a shared data store, and you could also pick a folder for it. We are going to skip that for now. Next, you define the management interface and then the interface for the individual Edge devices. So let's start with the management interface, which is going to be used to communicate between the control VM and everything else. So define the management port group, then configure the NSX Edge, provide the information about the routed interfaces. In our case, we are going to start with a transit uplink. This is going to be of the type uplink. Later on in the next video, we are going to attach an NSX Edge for that as well and provide north-south routing through that one. Click the plus icon to provide the primary IP address for the uplink interface. In our case, this is going to be 172.30.1.1 with a subnet prefix length of 28. We choose a smaller network for in this case because it's just for transit purposes and we will not need a lot of IP addresses. Next, we are going to add 3 interfaces just for our multi-tier applications. So we are going to use the web tier for the web applications. Again, the logical switch is going to be linked to this. Provide the primary IP interface for the distributed router, subnet prefix 24. So we choose a complete Class C network for that. Then we are going to add the DB tier. All of these 3 are internal, so the DLR knows that this is just internal traffic on the ESXi hosts. And Then we are going to click plus again, provide the IP network for this. So this is 172.30.12.1. So this is the final one, the apt here. IP address needs to be added, 172.30.13.1, subnet prefix. Then we provide a default gateway. We will work with static routing for the moment and will change into a dynamic routing approach at a later point in time during the material. So now that all of these parameters are set, we can actually hit the finish button, which is going to deploy the control VM for the DLR. And then we can actually start using the individual features. To configure the DLR, you can always double click on it, hit the Manage tab, and we are going to make one little change on the DLR because the default deployment for the firewall is everything is going to be denied. We are going to enable packet forwarding through the DLR, or in this case, we are going to basically allow all traffic through the firewall, which is a requirement in our case to provide you with the necessary scenarios. Configuring the distributed firewall can be a bit confusing at the beginning. For now, we are going to set this to accept and publish the settings. We will come back to this later in a chapter where we discuss firewalling. For now, it's just to allow us to get traffic through the system. Once the setup is done, we can actually connect to our web server and then open the console. And now we should be able to ping the DLR interfaces. So let's start with our gateway. So 172.30.11.1 works. Let's try the other gateway. So that's another IP and a server on one of the other networks. You can see here this works perfectly well as well. And we are going to do this on the other network as well. And okay, there is a missed packet at once, though, so it needed to learn MAC address and everything first. And then everything is fine. Let's take a moment to look at the console interface of the router and run a show IP routes there to see the static routes which have been automatically learned by the interfaces. Login is admin and then the password you provided during the install, and then you can just run a show IP route interface or show IP route command, and you will see here that all the interfaces are uplinked. In the next video, we are going to discuss the deployment of NSX Edge for north-south routing. In this video, we are going to discuss the deployment of the NSX Edge for north-south routing. This is going to be combined with what we previously did, the east-west routing with the distributed logical routing. So this way we are going to allow us to connect from our desktop machine over the NSX Edge north and south routing to the distributed logical router and then finally to our VM. In this video, we are going to take a look at how to deploy the NSX Edge and set up some static routing. First, select NSX Edges from the left-hand menu. Similar to the distributed logical router we deployed before, we are going to deploy the Edge Services Gateway or NSX Edge now. For this, you need to provide it with a name. We are going to call it North-South ESG for Edge Services Gateway. You can decide whether you enable HA, we leave that off. You provide a password, similar rules as for the NSX controller supply. And then you are going to enable the SSH access as well. Hit the next button. You can then pick the size of the Edge appliance. In our case, we are fine with the compact size. And then you pick where the Edge should be deployed, so the cluster and the data store for that. Hit the next button. And then you can specify the routing interfaces. We are going to start with the uplink interface, connect it in this case to the production port group. Then you provide it with the IP address. In our case, that's going to be 172.17.20.9 with a prefix of 24. And there's going to be the secondary interface, which is going to be the transit network, which is going to connect the north and south edge with the distributed logical router we provided before. Again, link it to the same network, so the transit network will be our linkage, and then you provide the IP address. In this case, this is going to be 172.30.1.2. Prefix length 28, same as on the other side. Once your interfaces are set, hit the next button, and then you can provide a default gateway for all default routing. We will provide that for the moment because we are going to do only static routing. Firewall will be all on the accept level, and then we are going to actually change that once we are going to deploy actual firewall rules in one of the later videos. Now that all of this is being set, we would expect that we can actually ping from our web server the distributed logical router, and let's try to ping also the edge gateway. This is still not working. Reason for that is very simple, because the edge services gateway doesn't know what is behind the DLR. For that, we are going to provide a static route for now, 172.30.8.0/21, which is going to include all the necessary networks, and then we provide the information about the DLR as our next hop with a transit uplink. Hit OK, click publish changes, and you will be able to see immediately that the routing of the packets go through. We can now also ping the external interface of the edge gateway, and we can also ping something on the internet. So you see, with that we have now fully connected our appliances behind our DLR. In the next video, we are going to look at how to combine the NSX edge with the DLR for dynamic routing with OSPF. In the next few minutes, we are going to combine the already set up NSX edge, which we are going to still use for north and south routing, and the DLR together with dynamic routing over OSPF. This is to ensure that you do not actually need to maintain all the manual routing entries. In this video, we are going to take a live look at a running environment on how to set up OSPF in NSX, especially how to enable dynamic routing with the NSX Edge and the DLR. Back in the vSphere web client, go to the NSX Edges, which is where we are going to make changes to our DLR configuration first. Double-click on the East-West DLR we created before. Go into the Manage tab and check that you have a transit uplink interface. Once you check that the transit uplink is there, go to the routing segment. And the first thing we need to do is create and provide a router ID. This is pretty straightforward, just actually select an uplink interface. Click Publish Changes to make the router ID active, which will enable us to do all the necessary OSPF settings. Switch to the OSPF area, hit the Edit button, click Enable OSPF, and provide all the necessary addresses. The protocol address is the interchange between OSPF routers, so that's the DLR control VM, and the forwarding address is going to be the IP address we are going to use to forward data from. Next, we are going to create a new area ID. In our case, that's 123. Once the information is published, we can also link an interface to the area. So in our case, the transit uplink will be linked to the area ID 123. Hit Publish Changes again, and we are good to go from an OSPF perspective. But we are going to also do some route redistribution for OSPF. Route redistribution is already set up. We just need to actually enable static routes on top of the connected ones as well. Click Publish Changes, and we are all set for the DLR. Switch again to the NSX Edges and select the North-South ESG for Edge Services Gateway. Click on the Manage tab, switch to the routing segment, and again, similar to what we did on the DLR, set the router ID in the global configuration. And once that is published, we can enable OSPF in the OSPF segment. Click the Edit button, click Enable OSPF, click OK. Again, we need to define the area ID. 123 is the area we are going to create here, and we can now directly link the interface to the area ID. So our transit uplink interface is going to be linked to the area ID 123. Click Publish Changes and the OSPF engine should be up and ready. The next step, what we have to do is we have to remove the static route we used in the examples before, which was responsible to route all the traffic between the Edge Services Gateway and the DLR. Switch to the route redistribution and enable route redistribution for static routes and connected routes. Next, we are going to take a look at the ESG and whether OSPF is up and running. We are going to switch to the console of the Edge Services Gateway, log into it, and do a show IP OSPF neighbor, and we can see that it's fully established. We can also check the IP routes. Let's do the same on the DLR. Again, log in as user admin and do a show IP OSPF neighbor. And again, we should see that this is fully established, and we should also see the IP routes we have in our environment. Finally, let's go to the web server again and see if we can still trace route or ping the Edge Services Gateway. So the real change in this environment is now that we switched away from the static routing, which we did before, into a complete dynamic routing. So the Edge Services Gateway will now automatically learn the networks created on the DLR over OSPF. And so even if you were to add a new network or something on the DLR, that change would be reflected via OSPF up to the Edge Services Gateway, and then you could actually do the routing from there, link that to your backbone, etc. With this trace route, we are going to just validate that this works. You can see here from the web server, we are going to first hit the DLR again. 172.30.11.1 is our gateway on the DLR, and then we hit the Edge Services Gateway external IP 172.17.20.9. In this section, we discussed several things. We showed you how to deploy an NSX edge for north and south routing, which is typically what we use for uplinks and stuff like that. And if you have a multi-tenant environment, you would create maybe one edge per tenant so that you can configure them. We also discovered how we deploy the NSX distributed logical router for east-west routing, so that is typically being used between your individual VMs. Finally, in this last video, we actually covered how to combine the NSX edge with the DLR for dynamic routing with OSPF. In the next volume, we are going to discuss a bit more about additional NSX edge services available by VMware.
Welcome to this video in Software-Defined Networking with NSX. This section covers load balancing with NSX. In this section, we're going to take a look at inline versus one-arm load balancing, and then we do a live demo of deployment of NSX load balancing. The first video covers the difference between inline and one-arm load balancing. Therefore, we're going to take a look at a load balancing overview and then take a deeper look into the difference between inline and one-arm load balancing. What is load balancing? Load balancing allows to access multiple servers using a single IP address, and an algorithm decides which server is used. The backend servers provide the same service. That is pretty important. So what are the goals of load balancing? First, to distribute the load across multiple backend servers providing the same service. This could be a website which is accessed using HTTP or HTTPS. A second goal of load balancing is to achieve a higher service availability. If a backend server fails, the load balancer notices that the server is no longer available and distributes new incoming sessions to different backend servers. Of course, sessions hosted by the failed instance are lost. We have a group of people accessing a service. This service is load balanced using an NSX edge with a configured load balancing service. So the users access the IP address or the name of the load balancer, and based on the algorithm, the load balancer distributes these sessions across different backend servers. About load balancers, they have a virtual IP address a VIP, and of course a port number to access a specific service. This could be a standard port like 80 for HTTP or 443 for HTTPS. These are pretty common services. We have a backend pool of servers providing a specific service. Each server within the backend pool provides the same service, like a website. Furthermore, we have a service monitor. This one checks if the service in the backend pool is still available. A simple ping test in most cases is not sufficient to verify if a server is up and running or not, because it just answers to the ping request, and that is not the best method in most cases. Lastly, we have the application profile. This one defines the service behavior in the backend pool. Like, do we need a session persistence because the application requires this specific configuration? What are the capabilities of the NSX load balancers? We have supported protocols. We can use a simple TCP UDP protocol, so we stick with layer 4 within the network, or we go up to layer 7 and use a FTP, HTTP, HTTPS. Within HTTPS, we can use either SSL pass-through or offloading. Offloading means that the load balancer handles the whole certificate stuff, and pass-through means the certificate is passed by the load balancer to the backend server, and this one takes care of the certificate. We have different load balancing methods. So round robin means we just distribute each session to a new server. Or we could use a source IP hash, so that the session redistribution is done using a hash value based on the source IP address. Or we just use least connections. So the backend server with the least connections will get the new request. Lastly, we have the URI HTTP URL header capability to distribute the new sessions. Additional capabilities are health checks. So we have TCP UDP ICMP health checks. So these are pretty basic. Or we have more advanced ones for HTTP and HTTPS. Within HTTP and HTTPS, we can use the get option and post method to call the web server and verify if the service is still available. We have session persistence on top of it. If we stick with layer 4 TCP, we can use either source IP or MSRDP. And on layer 7 with HTTP, we can use source IP or the cookie. And within HTTPS, we have aside source IP and cookie, the SSL session ID to achieve a session persistence. Session persistence means that if a single user with a single device accesses a backend service, new requests within this session will be distributed to the same backend server, and it's not switching backend servers. Within NSX and load balancing, we have two deployment modes. First, the one-arm load balancer, and second, the inline load balancer. The one-arm load balancer, we have a couple of users accessing a service somewhere in our infrastructure, and we have the NSX edge with routing or a DLR, doesn't matter in this case. For a one-arm load balancer, the NSX edge with a configured load balancing service is attached to the same network using an uplink interface as the backend servers are. So if a new request comes in from a user, the client IP address accessing the VIP address of the NSX edge, and this one performs both a source and destination NAT. From the load balancer, the NSX edge IP address accesses the server IP address in the backend, and the communication flow, the answer, is going exactly the other way around. So it flows from the backend server to the NSX edge IP address. Again, a source and destination NAT is performed, and the last step is the load balancer sends the answer back to the client IP address. Considerations about OneArm. It is really easy to deploy. As you have seen in the previous slide, you just attach an NSX edge with a single uplink interface to the same network as the backend servers are. So it's really easy to deploy. There's no need to do some advanced configuration on the edge. A slight disadvantage is using OneArm load balancers increases the number of NSX edges, depending on the amount of applications you want to load balance in the backend. But for each application, you need one NSX edge load balancer. It should be on the same network as the backend servers. From a configuration perspective and best practices, it's ideal to configure it that way. A disadvantage is it is not preserving the client IP address. So you can use the X forwarded header for HTTP to work around some issues with that, but the client IP address is not preserved. Let's take a look at inline load balancers. Again, we have a couple of users accessing a service in the backend. In this case, it's a huge difference because we have an NSX edge, or to be more precisely, we must use an NSX edge with a configured load balancing service. The uplink is configured to be accessed by the outside world, and the edge has an internal interface accessing the network of the backend servers. So if the client accesses the virtual IP address of the load balancer for a specific service, we use a destination NAT. The second step is the load balancer accesses, based on the algorithm, one server in the backend. But as you can see, the client IP address is still used to access the backend server. The flow back is exactly the same, so the server IP address sends the answer back to the client IP address directly, and the load balancer returns the traffic to the client from the virtual IP address. So as you can see, the client IP address is always involved in the whole communication flow if you use an inline load balancer. So there are a couple of considerations for inline as well. As we have mentioned, the client IP address is preserved. You can't do that with a OneArm load balancer. You can enable transparent mode if needed. The backend servers need to have the edge configured as their default gateway, because otherwise they won't be able to communicate back. As you have seen in the previous slide, the server in the backend sends the answer back to the client IP address, and that IP address is not on the same subnet, so the traffic flow goes by default via the default gateway. If this one is not configured, it's not working. The sizing of the edge is very important because we have routing and load balancing services enabled on the same device. In this case, please go to the NSX sizing guide to size the edge accordingly to the best practices. The next video will cover the deployment of NSX load balancing.
In this video, we are going to talk about the deployment of NSX load balancing. We are going to show you live how to do the basic configuration of the load balancing feature, and we are going to cover some of the failover scenarios as well. In this demo scenario, we are going to enable load balancing as part of the NSX edge. The idea is by enabling the load balancing on the NSX edge, we will split the traffic for the web server 01 and 02 so that each one of them will get an equal load. Be aware, as described before, that load balancing from an NSX perspective is not really looking at the load of the individual VM. We are just going to actually follow specific rules like round robin and other scenarios on splitting the load between the individual nodes. However, the availability piece is also always quite important. So in case one of the web servers would fail, all the other load is going to be distributed to the other one. So in this specific lab scenario, we are going to enable the load balancing feature for web servers with round robin enabled. We are not going to create a one-arm scenario. This is going to be a pure inline load balancing scenario. Once load balancing is set up, we will see that traffic coming actually from the lab desktop is going to be routed to each one of the individual web servers. So the first request would go to web server 01, second would go to web server 02, and so forth. This is as long as you don't enable any session specifics, so that you would actually go by source IP address or something similar like that. Let's start checking our web servers are both up. We have two web servers, one at 11, one at 12, giving us different responses so we can check that the load balancer actually works. Go into the NSX configuration, switch to the NSX Edge area, and then we are going to configure the north and south ESG. Load balancing currently is only available as a feature of the Edge Services Gateway. Switch to the Load Balancer tab and then click the Edit button to enable global features. Whatever you enable here is not automatically configured. This is just actually which features are going to be available as part of the global load balancer configuration on this specific ESG. Next, we are going to configure the application profile. The application profile defines the type of connectivity like TCP, HTTP, HTTPS, etc. And it also defines the persistence layer. For the moment, we are going to set this to HTTP with no persistence because we have static web servers behind that. We are going to come back to the persistence configuration later and actually show you the difference between the two. Now that the application profile is set, we can take a quick look at the default service monitoring features. Those are preset. You could actually change them, the interval, how often it should be checked, the expected results, the URL to check, but we are going to leave them as is. Next, we create a pool of web servers. So we give it a name, and then we need to also specify the algorithm we are going to use to switch between them, the health monitor we are going to use, and then you add the individual web servers. As we said before, we have two in this scenario. One is web server 01 and one is web server 02. We are going to set the port here for this specific scenario because later on I want to show you also the SSL offloading feature, and for that you need to specify the HTTP port here. You could also do actually path through SSL, but that's a different story. Okay, click the OK button and now you have your pool, your application profile. We finally need to define one part, which is the virtual server, virtual IP for the individual scenario. Click the plus button again, then you specify whether you want to enable that server. You give it a specific name. You select an IP address for it. And then you specify again the individual protocol you are going to use. We are going to start here with the HTTP protocol again for our scenario. IP address selected. You could also create your own IP address just for the load balancing feature. That needs to be done, however, before. You cannot actually do that on the fly while you create the load balancer over here. Once the virtual server is connected and configured, we can actually have another try and actually open the web page of the just set up load balancer, and you can see once we click the reload button that it actually switches between 01 and 02. Now let's enable session persistence, because in a real life scenario you don't want to have this switch just within a session. You can choose between cookie based and source IP based in our scenario. We are going to quickly use source IP based, and that will then show you that all requests will always bounce back to the same web server. This is necessary when you use application servers, etc., which don't have any additional clustering feature in the backend. So you can now see if we hit the reload button, it stays at web server 01. Next, we are going to create SSL offloading. We need to first create a certificate. You could also import one, but this is just a basic scenario, so we are going to create a self-signed certificate. But let's first generate the certificate request, so the CSR. You give it all the usual parameters for an SSL certificate, the common name, which is the web URL. We are using IPs here. Normally you would put your fully qualified domain name or short FQDN in here. You specify the organization name, unit, locality, state, country, whatsoever. and then you click the OK button. Now we have created a CSR. The next thing, you would normally actually send this to a CA and get your certificate. We are going to create a self-signed. In our scenario, we are going to say it's going to stay for a year. Now that we have a valid certificate in the system, we can actually go back to the load balancer feature, edit our web profile. We are going to switch this from HTTP to HTTPS next. And we are going to configure a server certificate, which is the one we just created. You click the OK button, and that's basically what you need to specify here on the application profile. We are going to check again on the web server pool. There is nothing we need to do here because we configured all the ports already. And then we are going to make a change on our virtual server. So in this scenario, we are going to now switch this to HTTPS. Be careful, it doesn't automatically switch the port number. And click the OK button. Now that this is done, we can actually go back and open our web page over HTTPS. And you see here that it actually complains about the certificate, and we are actually back on the web page. This is all good now. So this is SSL offloading. You could also do pass-through if you want to. Now let's actually take a closer look at one of the specific features for load balancing, which is failover. In our case, we are going to shut down now web server 01, which is the one we were just connected with. Once the web server is in shutdown, the web process will no longer react, and we can click the reload button, and we will see that we are automatically being redirected to web server 02, and we will actually stay on that one because that is for session persistence live now. Even after power on, this is not going to change. We discussed in this video the deployment of the NSX load balancing feature, but before we also looked into the different scenarios like inline and one-arm load balancers. Inline is actually what we did in this scenario. You had the load balancer, which we set up before. This sits between the client and the server. One-arm is a scenario which you would do actually to create a load balancer which sits beside the VM. In the next segment, we are going to discuss about the VPN feature of the NSX Edge Services Gateway. In this section, we are going to talk about virtual private networks, or short VPN. VPNs are commonly used to connect to private networks over an unencrypted, for example, internet network connection. However, they can also be used to connect a private cloud with a public cloud or similar scenarios. In this section, we are going to take a look at the NSX Road Warrior Access, Layer 2 VPN, and IPsec VPN. NSX Road Warrior Access is going to be our first example. We are going to take a live demonstration to take a closer look into the access we can provide with the SSL VPN feature. For that, in this video, we are going to take a look at how to customize and deploy agent-based VPN, and we are going to take a look on the agentless VPN features provided by the NSX Edge. In this live demo scenario, we are going to enable VPN Road Warrior services as part of the NSX Edge Services Gateway. For this, we are going to enable the service, we are going to create an IP pool and add the installation packages. We are going to demo you two different scenarios. One is the pass-through access with the SSL VPN enabled. In that scenario, the user is going to use a browser on his system to connect via an encrypted SSL tunnel to a specific website. Second of all, we are going to install an SSL VPN Plus client as part of the lab desktop system, which we can then use to access the network natively over a VPN connection. To configure the SSL VPN, go to the NSX Edges area of the networking and security part. Select an edge device, our north-south ESG. Select the SSL VPN tab. Select IP address, cipher list, and certificate. Hit OK, that takes a couple of seconds. This basically enables the basic configuration of the portal. Next, we need to specify the authentication method. In our case, we are going to just create local authentication. You could also link this back to an Active Directory LDAP, radios, or any other source. We are going to disable the password policy and the account lockout policy, etc. You could actually specify your own rule sets, and your users could actually later on make changes to IP addresses, etc. Click OK to enable this feature. Next, we need to specify a user. We are going to just create one specific user, in our case for this demo scenario. That user is going to be called VPN-user, and we are going to give it the usual password we use throughout all of the lab. Finally, we are also going to specify that this password never expired and that the user can actually change the password, which is set up as per default. Click OK. Next, we need to enable the SSL VPN feature. For that, we go to the dashboard segment and click the Enable button. Be aware that only one service can listen on port 443. So if you use the load balancing as we did in the previous section, you need to actually specify a different IP. Open the URL and you will see that you get to the SSL VPN portal. Log in with the just created user, and you will see an empty portal. So far, we can only change the password. There is nothing yet set up in it. Let's go back into the vSphere web client. There are a few more things we need to set up. First of all, we need to specify an IP pool, which is going to be the IP pool for the clients. Typically, we support from a NSX perspective up to 50 clients, so you don't need to make the range too big. We are just going to create some standard IP range. This should not be an IP range which you have in use for anything else. You specify a net mask and the gateway address. The gateway is automatically created on the NSX edge later on when the client is logged in for the first time. Beside the IP pool for the SSL VPN client, we also need to specify a private network, which is the area you want to access to. In our case, we are going to create access to the web servers, which was our 172.30.11.0 network. You could also add multiple networks. And then finally, we need to create the installation package. In our case, we are going to call this test package, and it's going to contain the IP address of the SSL VPN gateway. In our case, that's the NSX edge. We also specify in the test package some parameters like allowing remembering of the password, silent mode installation, whether a desktop icon should be created or not. That is all you need to do to have a custom client created. You can also customize a few more features. We will come back to that at a later point in time. Let's go back to the SSL VPN portal, log in again, and you can see we now have a test package here to download. You can actually run the setup from here. You might need to bypass the security. Click the Login button. Provide the user credentials for your VPN connection. And again, click OK. You now have an SSL VPN connection up and running. So now let's try to see if we can reach the web server. You can see once the VPN connection is established, we can now reach the web server. If we disable that feature again, and hit the reload button, you will see that we can no longer actually access the page. So you can see this is a rather straightforward and easy process to set up SSL VPN. A few more configuration settings are actually available. You can also specify whether a tunnel should be in full or split mode. So that means if all IP traffic is going to go through it, whether you want to actually upgrade the clients through the system. You could provide log-on, log-off scripts, which could also map network drives and other things. And there are some more generic settings in the system, like whether a user can use multiple logins, whether you want to see compression, logging, forcing the user to use the virtual keyboard for the password, how long the session should be established before it times out, and whether this is publicly available or not. So overall, some configuration settings you could use. And finally, you could also customize the portal with your own title, logo, colors, etc. So this is highly customizable. We also wanted to cover one other feature. So besides installing a client, there might be scenarios where you just want to make a web page enabled. So that is where we have the web resource feature. We are going to enable access to our web server 02 without installing a VPN client. So this could be helpful to provide users with a specific portal. Create that, and now you go back into the SSL VPN portal again. You log into the portal. And now you see there is a new web application, but let's go through it again. In the portal, you have your change password, the installable package, and you now have web applications in here. So you can just click on install web server and then you will see web server 02. So that shows clearly that we can actually make that available without installing a client. And you could also try it yourself. You cannot directly reach it. The next video is going to cover NSX Layer 2 VPN to bridge a Layer 2 connection over a VPN tunnel. This video will cover NSX Layer 2 VPNs. In this video, we are going to take a closer look at the use of NSX Layer 2 VPNs. Layer 2 VPNs are usually being used when we are connecting to networks, for example, a private and a public cloud, or to subsidiaries where we move workloads from one network to the other without changing the underlying IP infrastructure. So we basically combine two Layer 2 segments on both sides. This can be applied with NSX not only between two NSX sites. There is also a deployable NSX appliance which you could deploy on a different cloud platform. So for example, if you were to use your internal private cloud scenario and then you put the appliance onto an external site, connect the two with each other, and then you could actually bridge the same network between the two. Let's take a closer look on how this works in practice actually. In this live demo scenario, we are going to customize our demo environment quite a bit to demonstrate the Layer 2 VPN feature. For this specific scenario, which would be typically used when you have two different edges sitting in two different data centers to bridge a network, or you have a diverse data center infrastructure where you somehow need to bridge a Layer 2 segment across two different physical layers. In our scenario, we are going to deploy a new Edge Services Gateway on the .8 address of the production network. We are also going to attach the web tier to it, but this is going to be a secondary web tier. We are also going to create another routing interface for the web tier ending with a .2 address. This is never going to be really actively being used. It's just from a network topology perspective that we need to create that. In theory, your machines could use both gateway addresses in the end, but let's stick with the primary one. Once the secondary edge is being created and the network is being set up, we are going to remove the DLR pieces and directly attach our existing logical web tier to the first edge gateway, and then we are going to move the web server 02 over to the newly created edge. Normally these are now two separate Layer 3 segments per default. What we are going to enable then is the Layer 2 VPN feature, which is going to create and establish a Layer 2 VPN tunnel between the two different sites. Once that is established, the two VMs can actually communicate with each other without having to go through a router or gateway because we have that Layer 2 VPN in place. To create a Layer 2 VPN, we need to make a few changes to the lab environment we used so far. For that, we are going to switch to networking and security, select NSX edges from the left-hand tree, click on our north-south edge, and then we are going to add an additional interface. In our case, we are going to edit it because NSX edges always have all 10 interfaces pre-created. We only need to edit it. In our case, we are going to add an NSX trunk. So that is basically a combination of VXLANs within one network. So you basically connect an interface of an edge to a specific port group, which will then contain the networks. So we link this to the distributed port group, which was pre-created Layer 2 VPN trunk. This is not just anything specific, it's just a standard port group. Then you pick the sub-interfaces. In our case, we will only have one, but a trunk could actually have more than one interfaces, and this is basically to overcome the problem that edge devices only support up to 10 interfaces. So you specify a tunnel ID for that specific trunk. You specify the backing type, which stays to be a network in our case. You could also directly link a VLAN or something. And then you specify the logical switch you are going to link back to it. Plus, finally, you need to have the IP address. As this is a gateway, we are going to take the gateway IP address, which we normally would have on our DLR, and actually put it here. This is basically all we need to do from the interface perspective. Be aware that layer 2 VPNs are only supported with trunks at the moment, so you need to always create this, like in this scenario, only with one interface if you only have to link one layer 2 VPN. But this would actually allow you to link more networks as well. Once the trunk has been set up and enabled, you can actually switch to the VPN section. And then once within the VPN tab, we are going to select L2 VPN. And the first thing we need to do is enable it to be able to configure it. Once enabled, you can choose whether it should be a server or a client. We are going to start with the server, and for that you need to specify a few parameters, like the listener IP address. We only have one, so we stick with that. You can specify the port and the encryption algorithm, and you could also pick your own custom certificate if you want. Click OK, and now you need to, in the next step, create your peer site. This is basically linking back to your other layer 2 VPN site. So we are going to call this one L2 VPN headquarter. So that's the L2 VPN between headquarter and data center 2. User ID is VPN user and our specified password. You can completely select whatever you want here. And now you select your trunk interface, which you created before. Click OK and be sure that you don't forget to enable the interfaces. Click Publish Changes and you are good to go. That is basically all you need to do on the server side. Now we are going to create or deploy another edge device which is going to represent our client side. This could actually be on-site, like in this scenario, but you could also actually use an OVA, which VMware provides, to deploy a layer 2 VPN over a different site. Again, similar procedure as we have seen before. You just give it the name, the administrative credentials on how to log on to the system, specify whether it should be SSH enabled or not, size of deployment, then you pick the appropriate resource cluster or resource pool. We are going to put this in the resource cluster in our scenario here, which is going to represent our data center 2. You pick the shared data stores, click OK, click Next, and then we can also start specify the interfaces in our scenario. This is going to be pretty straightforward. We will only specify the uplink interface first. The other one is going to be our trunk interface, which we need to define once the edge is being created. We link this against the production port group, like what we did for the other edge devices before. You then click the plus sign, specify the IP address of the specific edge here, which is going to be 172.17.20.8, and a subnet prefix, and we are good to go with this interface. So you can just click OK. Then we can click basically Next and define the default gateway for our scenario, which is going to be. Click Next, click Configure Firewall Default Policy, click Accept, click Next, click Finish, and your edge is going to be deployed. This is going to take, depending on your environment, between a couple of seconds and a few minutes. Once the edge is deployed, you are going to go into the Configuration Settings interface, and then you are going to specify a trunk like what we did on the primary edge already. So we are going to call this L2 VPN trunk client. It's of the type trunk again. We specify the port group for this, which is going to be used for the transfer. Click OK. Then you specify the sub-interfaces which are going to be used. So in our case, again, we are going to create a sub-interface to web tier. Tunnel ID is going to be identical than what we did before. We select the logical switch for it. In this case, we are going to switch a different one. So this is not going to be web tier again, because we want to simulate the scenario that we have two logical switches. We are also going to provide a manual IP address for the gateway part, which is not going to be actually used by the devices. It's just more or less for reference purposes. However, you could actually specify for your individual VMs on both sides each one of the gateway IPs. Next, we need to enable the layer 2 VPN service here as well. Click on the client area. So it's a client specification now. And the next things are the basic configuration for the client. Pretty similar to the server. The only difference is you now specify how to reach the server, pick the port, pick the proper cipher algorithm, select the port group or the trunk interface we created before. And then that's basically all you need to do. You can also specify the user, or you need to specify the user ID, the passwords, and then this is going to be all. Click OK, publish the changes, and then you typically wait a couple of minutes and the status of the tunnel will switch from down to up. And once your tunnel is up, so this can take somewhere between 5 seconds to 30 seconds or whatever, and then the tunnel is going to be up and you are ready to transport some frames over it. So to really test this scenario now, we are going to actually specify the logical switches for two VMs. So we first want to be sure that our web server 01 is still connected to the web tier, so we are going to re-add it. It should still be there from the previous examples, but just to be sure, click the web server, hit the right arrow, select the network interface, click Next, click Finish, and then we are going to specify the other web tier, which is on the Data Center 2 side. Click Actions, Add VM, and link our web server 02 against that specific port group. Again, ensure that you select the network interface for this. Otherwise, it's not going to be transferred. Click Next, click Finish, and we now have our two web servers on two different logical switches attached to two different separate layer 2 VPN edges. What we are going to do next is we open the console of web server 01 and see if we can still ping web server 02. That should actually only work if our layer 2 VPN is up and running. So for that, we are opening a console prompt, switch the ping command to be 172.30.11.1, which is our gateway that is reachable, and we can also still reach 172.30.11.12. So we can see web server 01 and 02 can still talk to each other. In the next video, we are going to take a look on how NSX with IPsec VPN is going to work. We are going to cover next routing and IPsec-based VPN with NSX edges. In this video, we are going to take a closer look at a live demonstration on how to set up routing and IPsec-based VPN with NSX edges. When we use IPsec-based VPN, we have the advantage that we can actually link NSX edges with all kinds of other firewall and VPN systems. Every other system which can do IPsec-based VPN can be linked basically against an NSX edge. When you are going to set up IPsec-based VPN, you need to always consider the amount of traffic and the number of connections you are going to push through the system. For that, VMware provides a design guideline on how to size the NSX edge appropriately for it. If you want to provide some higher availability, you should also consider whether you set up NSX edges in an HA mode for this to work perfectly well. Another point when you are going to use IPsec-based VPN is the offloading to the physical CPU based on AES NIH chipsets on the Intel CPUs, which is basically standard on almost all current server CPUs. In this demo scenario, we are going to revert what we did before with a layer 2 VPN scenario. For this, we are going to move the web server 02 back to the original logical switch for the web tier. Once that has been done, we are going to remove the newly created web tier on the logical switch number 2 and on the Edge Services Gateway number 2. And we are going to reattach to that Edge Services Gateway number 2 our database tier. So that's the logical switch which we created earlier, and that logical switch also has the database server attached to it. Once this has been set up, we are going to establish an IPsec VPN tunnel, and we are going to route the traffic between the two Edge Services Gateway. For sure they are sitting in the same network, but this is just showing the principles on how communication would be done. So what we have seen in this demo scenario is how to build a rooted classic IPsec VPN tunnel. In the previous scenario, we used a layer 2 VPN tunnel to bridge two network segments together. First, we need to make some modifications to our existing configuration. We are going to start by removing some interfaces and moving them to other devices. So first, we have to go to our distributed logical router from the previous videos. And in this specific scenario, we click on Manage and then on the interfaces, and then we are going to remove two interfaces from the system. The DB tier, which will be part of our so-called Data Center 2 node, and as well as the web tier, which we also will replace and actually move that to the ESG, so it will be part of our primary data center but located at the primary ESG. Next, we head on to the Edge Services Gateway on our primary site. We go to the interfaces area, and then we need to actually add the just removed web tier interface here. So this is pretty straightforward. We provide it with a name. We select the distributed port group, or in our case, the logical switch. We then provide the IP address for this specific scenario, so 172.30.11.1, which is basically what we removed from the DLR before. Specify the subnet mask, and then we have the interface. Next, we configure the VPN part. So for that specific scenario, we are going to give the VPN tunnel a name. DC2 VPN, we provide it with a local ID, the endpoint, which is the IP address of the local site, the local subnet, that's going to be our web tier, so 172.30.11.0/24, and then we specify the other side of the tunnel, which is going to be our data center 2 with a peer endpoint 172.17.20.8, so it's in the same network, but it could also be routed, and then we provide the peer subnet, which is the DB tier, so 172.30.12.0. We are going to use a pre-shared key here. You could also actually use a certificate-based authentication. Enable the VPN config, click the publish, and that's basically all you need to do on this side. Next, we are going to deploy another ESG for our data center 2 side. So for that, we hit the plus button in the NSX Edges area. You provide it with a name, so it's going to be called Data Center 2 ESG for Edge Services Gateway again. And the Data Center 2 ESG is going to be, again, deployed as an NSX Edge. You provide it with a password, same procedure as we did before. And we are also going to enable the SSH access to it so that we can be sure that all of that works. We then provide the requirements on where to host this. So this is going to be part of the resource cluster. Within that, we are going to actually pick a shared data store so that in case of an HA event, etc., it's going to be restarted. We provide the interfaces. We start with the uplink interface. So this is basically the IP network we are going to use to link the two edges to each other. So it's going to be on the REST production side. We are going to provide a primary IP for that specific case, 172.1720.8/24. And we are also going to add the DB tier. So the idea behind this scenario is that we actually link the web and DB tier over the VPN tunnel between the two ESGs. For that, the DB tier, which we removed from the DLR, needs to be part of our new VPN site on the data center 2. Provided with a gateway IP address, so all the stuff we removed from the DLR, and we are also going to provide a default gateway in our case. Firewall will be all on accept for the moment. And that is basically all we need to do. Click finish and wait for the ESG to be deployed. Once the ESG is actually deployed, we can log into the ESG, go to the VPN area, and basically what we enter now is just the opposite on what we did on the other appliance. So it's pretty straightforward. So in this scenario, we are going to give it a tunnel name, so that doesn't need to be identical, but from a naming perspective that makes sense. Local ID is what the peer ID was before, so DC2, the IP address of the uplink interface, the DB tier, local subnet, and then we provide the peer ID information for the other side with the web tier network for that specific area, and then we need to provide the same pre-shared key. Again, certificates would be possible as well, but then you need to first set them up. And then you click the OK button and we are off, good to go. Click Publish Changes, and then it should take a couple of seconds, and the IP tunnel in most cases should be immediately up. As you can see here, channel status is up. So the next is we are going to log into our web server VM and going to try to do a ping from the web server to the DB server, so over the VPN tunnel. Open the console of the web server. We are going to log into the web server appliance. And then first of all, let's ping our local gateway from the web server. We are going to try the local gateway on the other side from the DB tier and the DB server as well. You can see here, you can perfectly well ping between all the individual systems. Let's actually just do a secondary check. We are going to go back to the VPN configuration, click the Disable button, click Publish Changes, and you will immediately see if we go back to the remote console that the client is actually no longer able to ping the other side, so the VPN is obviously in place. In the last few videos, we covered 3 VPN topics with the NSX. One was the NSX Road Warrior access, where we use SSL VPN to allow users to access an NSX environment over either an SSL VPN client or directly web-based without an agent. We also covered the NSX Layer 2 VPN, and finally, in the last few minutes, the NSX IPsec VPN.
Welcome to Software-Defined Networking with NSX. This section covers firewalls in a modern SDDC, a software-defined data center. In this section, we're going to take a look at why do we actually need a different firewall approach, the different options we have with NSX Edges and a distributed firewall, and the third part will be the concept of the service composer, security groups, and we will cover micro-segmentation. The first video covers why do we need a different firewall approach. In this video, we're going to take a look at the evolution of the firewall and what has actually changed. Let's discuss the firewall approach in the physical world. We have an internet connection and a physical firewall box. Within our own infrastructure, we build a couple of physical servers. We have a switch to transport the network traffic within an IP subnet. We can build another IP subnet, which is pretty basic, and between these two subnets, we are going to use the firewall with its rule set to take care of the traffic. In this case, the firewall is configured as a default gateway for all the physical boxes. If we are going to add another server to IP subnet 2, and we made the decision that we need a firewall in front of this server, it is not possible because you can't have a firewall within a single IP subnet. You need to have a default gateway. In this case, you need to configure a new IP subnet, move the server, do the re-IPing, and that enables you to create firewall rules on the physical box and have the traffic inspected. So that's basic for physical firewalls. A short recap about virtual networks, the virtual switch. Within the ESXi, we have the virtual switch. The virtual switch leverages physical uplinks to pass traffic between the virtual and the physical space. We have covered that in the previous module. On the virtual switch, we have the ability to create different virtual machine port groups and attach virtual machines to these port groups. Different port groups can coexist on the same virtual switch, and we use them, for example, different VLAN IDs. Additionally, we can create VM kernel ports. VM kernel ports add features like management traffic, allows the ESXi to access an IP-based storage, or, very important, to use vMotion, plus vSphere replication, vSAN. All these different kinds of traffics are covered by VM kernel ports. By default, the virtual switch has a configuration which consists of lots of settings. And by default, all these settings are inherited to the virtual machine port groups and the VM kernel ports. You can break the inheritance and do a specific configuration on a port group or a VM kernel port, but that's the default behavior. A short recap about the distributed virtual switch. We have our vCenter server with its DB. We have, in our example, 2 ESXis. If you create a new distributed switch, the whole configuration is owned by the vCenter server and stored in the vCenter server database. A pretty simple explanation about the distributed virtual switch behavior is this configuration is sent to each of the ESXis participating in this distributed switch, and each ESXi creates, based on this configuration, the distributed switch plus the distributed port groups. The difference between the distributed switch and the virtual switch or standard switch is that the distributed port group owns the whole configuration, like security settings, traffic shaping, VLANs, and the teaming and failover policy. The distributed switch does not have as much configuration options like the virtual switch, but the distributed port group has more options than the virtual switch. The firewall approach in the virtual world. Again, we have our internet connection and a physical firewall box. On the left-hand side, we create the virtual space. We have a couple of ESXis and some virtual machines, and we just created 2 VLANs. In the physical space, we have another switch and 2 physical servers. If a virtual machine would like to communicate with a physical server, the forwarding process or the traffic flow is straightforward. So what happens? The virtual machine sends the network traffic to the physical firewall because the physical boxes reside on another subnet. So we need to use the default gateway. The firewall itself inspects the traffic based on the configured rule set, and if allowed, the traffic is forwarded to the physical server. So in the end, there is not a big difference compared to the physical approach we covered a couple of slides ago. The big difference is, what if a virtual machine wants to communicate with a virtual machine on a different VLAN, which implies a different IP subnet? So the traffic is sent to the firewall again, because it's a default gateway, and again the firewall inspects the traffic. And now the clue is, the firewall, if the traffic is allowed, injects the traffic into the different subnet and passes the traffic to the virtual machine. The worst case scenario would be that both virtual machines are running on the same ESXi. That implies that the traffic goes via the uplink to the firewall and back, probably using the same uplink into the ESXi. So that produces lots of overhead or network bandwidth utilization on the physical uplinks on the ESXi. Last but not least, something we should cover are in-guest firewalls and antivirus solutions. If we have, and it doesn't matter if it's a virtual machine or a physical server, but in our case we cover virtual machines, you have the ability to configure a guest OS firewall. It doesn't matter if it's a Windows or a Linux, both systems have these capabilities. You can use a centralized management for these firewalls. Within Microsoft, you could use the group policies to configure these firewalls, for example. So you have a centralized management, so that's good to go. The disadvantage of in-guest firewalls is the traffic is analyzed after it has entered the OS, because the traffic needs to go to the TCP/IP stack of the OS, and then the firewall kicks in, verifying if the traffic is allowed or not. So that's a disadvantage using in-guest firewalls. Same with antivirus solutions. You can install an antivirus solution, you have a centralized management as well for these, but if you update your antivirus solution, you produce tons of load and you really have huge load on the infrastructure, its CPU, its memory, and of course it is the storage system, because you need lots of I/O to update all these applications. So that's a short cover about in-guest firewalling and antivirus. Let's go to NSX. NSX firewall basics. First of all, NSX allows us to use or do something we call microsegmentation. Microsegmentation basically means that you have one firewall instance per virtual machine. So the idea behind that is that we move the firewall closer to the VM. NSX also allows third-party vendors to develop additional solutions, like more advanced firewalls for layer 7, or we're able to integrate centralized antivirus solutions instead of having an installed AV solution within each virtual machine. That reduces the traffic or the workload overhead a lot. Let's cover the firewall approach within NSX. Again, we have the internet and a physical firewall box, and we created 3 IP subnets with a couple of virtual machines. So the easiest approach, or what we have done in the past, was the following. We just connected all these networks to the physical firewall using VLANs, and each of the virtual machines had the physical firewall configured as their default gateway. As we move further in NSX, and what you have seen in the past videos, is that we have something we call a DLR. We can connect the DLR to a physical firewall. But using a DLR does not end any security to the infrastructure, because as we already know, routing does not imply security. Routing is just straightforward packet shipping, that's it. If the DLR has an interface within a network, it routes, full stop. We could move firewall functionality to this piece of the infrastructure, but the DLR doesn't have any firewall. So in the end, that would be an NSX edge and not a DLR anymore, so we could use an edge. So as you see, we are not replacing the physical firewall. So the idea is to add more security to the infrastructure and reducing load on the physical firewall. So that would be an option, but it's not the best solution. What NSX provides is something we call the distributed firewall. That means we add firewall functionality to each virtual machine, or to be more precisely, to each virtual NIC. The next video will cover the different options between the NSX edge and our distributed firewall.
Welcome to this video in Software-Defined Networking with NSX, talking about the different options we have with the NSX Edge and the DFW. In this video, we're going to take a look at which level of protection is applied at which layer. Let's start with a comparison between the NSX Edge and the distributed firewall. So DSG is a virtual appliance form factor, which is basically a virtual machine with a pre-configured OS, tools, software applications, CPU, memory, and network interfaces. So the DSG is limited basically to 210 NICs, because that is the limit of a virtual machine. To use the ESG as firewall, it needs to be configured as a default gateway, and that configuration is done within the guest OS of the virtual machine. So the TCP/IP stack of the guest OS needs to talk to the ESG as default gateway, so it's not transparent. It can be used in conjunction with other built-in services, like the routing or VPN, NATing, load balancing. The DFW, on the other hand, it is a kernel module, this placing the service a lot closer to the virtual machine. The DFW is fully transparent to the virtual machine, and that's one of the pretty cool features. It is firewall only, so the DFW does not contain any other features than firewalling. And it can be used without VXLAN. So the DFW is the only feature we have within NSX, which could be used as a standalone feature. The DFW provides firewalling within a single IP subnet, and that is one of the awesome things of the DFW. So the firewall is fully transparent, and you can do firewalling within a single IP subnet because there is no need to configure the DFW as a default gateway like you have to do with an ESG, and that adds lots of security to your data center. So let's do a layers of protection overview. We divided the screen into two pieces, the virtual space and the physical space. So we have the perimeter firewall, which is a physical box because it's connected to the internet, and somewhere in the infrastructure we have a physical router. Attached to the physical router we have different networks, and we just added a couple of VLAN IDs like 783 or 539. So these are physical networks, and physical servers are attached to the physical router. In virtual space, we connect an ESG to the physical router, and behind the ESG we use a DLR, and the DLR has all the networks connected of the virtual machine. So we just added 3 VNIs in our example. So let's focus which layer of protection is placed at which layer within the data center. So first we have the perimeter firewall. This physical box is responsible for blocking the traffic from the internet connection and just allows traffic passing through the firewall to our infrastructure. The second layer we have is the ESG. So the ESG is kind of a border firewall, or you could say a perimeter firewall for a virtual space. So the ESG filters traffic which is only allowed to travel into the virtual space. And the third layer we have is the distributed firewall on the virtual machine. So what happens in the space here? So the physical servers are using the perimeter firewall for security. So on the one hand, you have the router, but as we have already mentioned, a router is not adding any security to your infrastructure. So if you want to make sure that traffic between two physical networks is secured by firewall, the firewall needs to be the router as well, or vice versa. On the other hand, it allows us to keep traffic within the virtual space. So what we can do is we secure virtual machines using the distributed firewall, thus allowing the traffic to stay inside the virtual space, and there is no need to use the physical router or a physical firewall. So we reduce the CPU and bandwidth needs on the physical devices. The NSX Edge Services Gateway has a couple of different built-in services. We have routing, VPNing, we have NATing, could use a load balancer, inline one arm, or a firewall. So these features can all be enabled within DSG. Let's now focus a little bit on the firewall. The DSG firewall, as we've already mentioned, to use this one, a virtual machine needs to have the ESG configured as default gateway, and this configuration is done within the guest OS of the virtual machine. And then you just create the rule set. It is completely similar to a physical firewall box. You add a rule and then the traffic is analyzed. So it consists of a rule ID, a name. I just used rule 1 and rule 2, not highly creative, but it's good for the example. The type defines where the rule comes from, either from a user, that's when an administrator creates a new rule, or you have default rules, they come from the system or from the default configuration. And then you just add a source, the destination, the protocol, and the action, what's with that traffic. The ESG is exactly the same, like a physical firewall. We have incoming traffic, and that traffic is matched against the rule set. And the rule set is passed from top to bottom. So the first rule matches for a specific traffic is used. So you should spend a lot of time designing your rule set on the ESG, and the behavior is exactly like a physical firewall box. The distributed firewall, on the other hand, is on a per VM, or be more precisely on a per VNIC per VM base. So we just add a virtual machine. The virtual machine has a virtual NIC and is attached to either a virtual switch, a distributed switch, or an NSX logical switch. As we have mentioned, the DFW is completely independent from an overlay network. So what we could do is, or if we add another NIC to the virtual machine, the distributed firewall instances itself another time. So there is one DFW instance on a per VNIC base. The distributed firewall rule set. That's a pretty cool thing about the DFW. So again, we have our rule set. It looks completely similar to the one before, but the problem is, as we have mentioned, the rule set is passed from top to bottom. So if you add the rule set to each DFW instance, you would have lots of firewall instances needing to pass a huge rule set. So let's do a short example. We have 3 virtual machines connected to one logical switch within NSX. So what's happening in NSX is, with the DFW, the rule set is matched against the object. So the source, we start with VM1. The source is, for the first rule, it's VM1, and the third rule, it's the any block rule. So what happens is, only these 2 rules are applied to the distributed firewall instance of VM1. And it happens exactly the same with virtual machine 2. So you have the source, like VM2, and any. So these 2 rules are attached to the firewall of VM2. And the same happens for the third virtual machine. But there is no specific rule for the third virtual machine. So the only rule we have is the default rule with this any block. So there is only one rule on this DFW instance. The cool thing about this, the rule set in huge enterprise environments, you might have a rule set with 1,000, 1,500 or more rules. But each DFW instance per virtual machine has only a subset of the rules, allowing the DFW to walk through the whole rule set lots faster, and that reduces the overhead. Another cool thing is the virtualization context awareness. So if you have a physical firewall, and of course, as you see in all our examples, we use the zero trust model, you create the rule. Let's say the first rule, you have a source IP, a destination IP, and a protocol. And you allow specific traffic, in our example, HTTP. So that's done in the physical firewall. Or another rule, you could have, instead of using a single IP address for source and destination, you could use a network, in our example, a /24. Or you can, instead of using layer 3 and layer 4, you can go down to layer 2 using MAC addresses or MAC ranges. So that's how you configure a physical firewall, and I hope you're familiar with that behavior. But what's the cool thing about virtualization context awareness within NSX? If you create a rule set, either ESG or DFW, like this, you can use many different objects instead just using IP addresses or MAC addresses. So we have lots of different objects within the vCenter server inventory. So what you could do is just use NSX logical switches as source and destination. So what happens if you connect a new virtual machine to one of these logical switches? It automatically gets this rule added to the local DFW instance rule set. Another possibility, you'd grab virtual machine folder, right? So you can organize the virtual machines into folders within the vCenter server inventory and use these folder objects as a source within a rule. And as we all know, virtual machines are running on ESXis and they can be organized into cluster objects. So you can grab one of these cluster objects and add it as a destination. So you have a rule saying each virtual machine as a source sitting in this specific folder, and they're allowed to talk to virtual machines running on that specific cluster with the protocol. So that can be used for Oracle, for instance. You can use Active Directory uses and data center objects. You can create rules based on the logged in user within the guest OS. Or if you have virtual machines, and as we have already mentioned, a virtual machine can have more than one VNIC. You can use single VNICs. So you can secure very specific network regions, and if a virtual machine is connected to more than one network, you can add rules for just one of these specific networks. And last but not least, we have security groups and ESXis. So security group is just a collection of virtual machines or a grouping of virtual machines using a couple of criteria like the OS name or the type of the virtual machine. Is it a Windows or a Linux-based VM? So you can use security groups and they have dynamic membership, which is awesome. So you can use like, oh cool, I create a very specific rule subset for Windows-based virtual machines, and if a new virtual machine with the setting Windows is created, so it's the OS name, it automatically gets the rule set for Windows VMs. So that's virtualization context awareness. You can apply a single rule on the DFW and the ESG at once. So if you just create a new rule, and we just grabbed a screenshot from the lab infrastructure, you create a new rule, and the new rule is like, oh my God, I want to have that rule on the DFW and one or all of my ESGs as well. You can click over here. There's a small pencil icon, which is not shown in the screenshot. So you click over here, and then you get the apply to wizard. And you can select apply this rule on the DFW, yes or no, or apply the rule on all the edge gateways. Or if you have many ESGs, you just select one of your or a couple of available objects of ESGs, add it to the select objects and click OK. So you can add the same rule to various layers within your data center. The next video will cover the concept of the service composer, security groups, and discusses microsegmentation. Welcome to this video talking about the concept of the service composer, security groups, and microsegmentation. In this video, we're going to take a look at what are security groups, how are they applied or used. So the concept of the service composer, it allows administrators to select multiple objects at once and apply firewall rules, endpoint protection, and or network introspection to this group. So what are security groups? A security group basically defines who is going to be protected. So it allows administrators to select virtual machines based on specific properties. A security group can contain data stores as well or different other objects, but in our example, we stay with virtual machines. So how does it work? We have lots of virtual machines within our infrastructure, and these virtual machines have lots of properties. So what we do in this example, we focus on the OS. So you can divide virtual machines into two main groups, and that could be done using the OS. So we have Linux-based virtual machines and we have Windows-based virtual machines. And based on that type, because the OS type is configured during the creation of virtual machine, either create a new virtual machine or just use a template, but in the end it is a known property. And you can use this property and define a dynamic membership criteria saying, please add all virtual machines which have a Linux OS and add all virtual machines which have a Windows OS configured. On top of the dynamic membership criteria, we have something we call a static inclusion. Maybe you might have an object which needs to be a member of the group even though it has not this property set. Or you can use a static exclusion saying, I have an object matching the criteria, but I don't want to have it as a member of this group because I want to apply something which is not useful for this single object. So that is just one example. Another one could be just use tags. So we create 3 security groups and they have a dynamic membership criteria saying, please add a virtual machine with very specific security tag. So we just create a virtual machine and add a tag to this VM. So it is immediately moved into the security group. A tag can be changed to the red one in our example, and the virtual machine immediately is moved to a different security group. Or you can change the tag as well and it is moved to another group. So this is highly useful for automation within your infrastructure. So we have defined security groups and how you can add, or we did 2 examples how virtual machines can be members of a security group by dynamic stuff. But on the other hand, we need a security policy. As we've already mentioned, the security group defines who is going to be protected. On the other hand, the security policy defines how will it be protected. And the security policy contains firewall rules, guest introspection services, and network introspection services. You can use just one of these 3 per security policy, or a combination of, or all 3. So everything is possible. How are security policies used? We create 2 security groups in our example and apply a security policy to the security group. The dynamic membership criteria for these 2 security groups is tagging. So we have a green and a red tag. Now we create a virtual machine. How can that virtual machine be a member of the group? Yes, you just add the security tag to the virtual machine. So if you add the green tag, the virtual machine is placed into the green security group. The cool thing about tagging is, if you add a second tab to the virtual machine is member of both security groups, and therefore it gets both security policies applied to this object. Thus allows you to create highly complex security policies and service combinations for a single object. Microsegmentation within NSX. Let's do a short definition. Microsegmentation transforms the network into smaller, application-centric segments which are firewall separated and prepared for automation. Let's go a little bit further with microsegmentation within NSX. So the implementation in the past, we had a physical firewall, couple of different virtual machines, and we need to make sure that the virtual machine traffic is sent to the firewall so that the firewall is able to do all the rule checking and verifying if virtual machines are able to talk to each other. Therefore, you create a rule set, source, destination, internet, web, and so on and so forth. Within NSX, we have the ability to have an edge, we create a DLR, and then we add different networks. So the implementation can be done in 2 ways. You create a tier per service, like it's shown on the left-hand side, or even cooler, you have all 3 tiers from our application inside a single network. And then you create a rule and use security groups, saying the source, for example, the internet, is allowed to talk to the web server, and the web servers are able to talk to the app, and the application is able to talk to DB. So the whole segmentation is done using the distributed firewall, even though all 3 virtual machines reside within a single IP subnet. So that is kind of a boxed application, and that can be reproduced. So we have the sources and the destination security groups, and the machines we just use a dynamic membership, like if it is a web server, please add it to the security group. And now you can reproduce that. We create a new network, have a web app and DB server, and you do the 3rd time. You can do it as often as you like. And that leads us directly to automation. So we have users, and these users access a self-service portal, for example, vRealize Automation. And based on the stuff we have discussed on the previous slide, the self-service portal plus VRA is used to automate the whole deployment, and that allows you to create the exact same application many times and have a lifecycle management on top, and everything is automated, including the destroy of an application. So in summary, we did why do we need a different firewall approach within the SDDC and the evolution of the firewall. We have discussed the different options we have with the NSX Edge and a distributed firewall. And in this video, we covered the concept of the service composer, security groups, and microsegmentation. The next section covers the deployment of the different NSX firewall technologies.
In this section, we are going to discuss the deployment of NSX firewall technologies in a live scenario. We are going to take a closer look at the NSX Edge firewall, the NSX distributed firewall, and finally the service composer feature. We are going to start with the NSX Edge firewall. In this live video, we are going to take a look at how to enable the firewall features on the NSX Edge and how we create some rules for NSX Edge firewalls both on the Edge device itself and in the generic NSX settings. In this demo scenario, we are going to enable the firewall services on our Edge Services Gateway. Or to be a bit more clear, we are going to actually switch from an allow all to a zero trust model. For this, the firewall service is going to really be activated in our case, and we are going to create a new firewall rule, which is once we establish the zero trust model, which is that we always have a default rule which is going to block everything which has not been explicitly allowed. We are going to create a new rule, and that rule is going to allow any kind of HTTP or HTTPS traffic to our web servers. Any other traffic coming from the production network through the Edge, for example, accessing directly the app server or DB server, would no longer be possible. They would still be able to communicate with each other because the three tiers down behind the transit network are actually connected with each other over the DLR. There is no distributed firewall so far established, so we would only do outbound communication filtering with a firewall on the Edge Services Gateway. There are multiple ways on how to apply an Edge firewall, but first let's check again if our web servers are reachable. So we are going to start accessing web server 01. We can clearly see it's currently available, and we are going to access web server 02 as well. So first of all, we take the classic approach. So we are going to go and connect to the NSX Edge and then do the firewall configuration on the actual Edge. This has been the rule on how to configure firewalls with VCNS and NSX up to version 6.1, and with 6.1 we have a different way for that, which we are going to cover later on as well. First of all, in the previous examples, we set the firewalls to allow any traffic. So the first thing is we are going to change this from accept to deny. So all traffic as of now is going to be blocked by the firewall as soon as we publish the firewall rule set. So once the publish is completed, we can actually connect to our web service or try to connect, and we will see that the connection is now going to fail. So that's the attempt for now. So the next step we are going to take now is to create a new firewall rule which is going to allow the traffic for the web server. In that specific scenario, we are going to click the plus for the rule name so that it has a clear description where we are going to tell the system that we are going to allow web traffic. This is for more or less description and documentation purposes. I typically, in a real-life scenario, would also suggest to put a ticket number or something in here. Next, we specify the destinations. You could specify the destination by all kinds of different ways, but let's start with the services. So the service by itself is HTTP, HTTPS. Those are the two services we are going to allow for these specific web servers. Click the OK button, and the services are configured. Next, we are going to define the destination addresses, which are going to be our virtual machines. There are multiple different ways on how this could be done within NSX. You could use the classic approach like with every other firewall where you would actually specify the IP addresses, but we are going to use objects which we have in a vSphere environment anyway. So you could actually use your virtual machines. We will also cover later on how you could use tagging and other features to provide firewall rules for your machine. So we now have created a rule which says web server 01 and 02 with HTTP and HTTPS are going to be accessible from the outside. Let's try again if we can connect to our servers. So web server 01 is reachable again and web server 02 as well. So this was one approach on how to configure the firewall rule sets. The disadvantage of this approach is actually that whatever we do here from a rule set perspective needs to be done on the appropriate edge device. So this can be quite complicated to maintain because it's not really better than what you have in a real life scenario where you would have hundreds or thousands of different firewall appliances. So let's take a closer look on how we could do this a bit more intelligently by setting up rules on the overall vSphere environment and let NSX control where the firewall rules should be applied. So first of all, this works only with NSX version 6.1 and above. And you can select the firewall area. And the first thing we are going to do now is we create a section. Sections are good because they help you to group individual firewall rules in your environment. So our firewall section is going to be called web server. You see the system has automatically created that at the top. And the next thing is now we can create a rule set within it. You also see behind the name and with a number of rules, how many rules are involved in that specific section. Once you unfold the section, you can again see a similar rule set like what we have seen before within the NSX Edge definition. We are going to give this specific rule a name again, allow web traffic. And then we are going to specify the destination and the services again. Again, we are going to pick the destination VMs because that's easiest for us here for now. Again, you could use all kinds of other rule sets for this as well, but we will come back to some of them in later examples. And then beside the web server, we are also going to specify which services should actually be specified. So that's going to be HTTP, HTTPS again, like what we did before with the Edge firewall. You click OK. And this first attempt is actually going to fail actually. Publish changes is going to provide the firewall rules in the infrastructure. The challenge we have now is that our edge device is actually set to deny everything, and the default for overall firewall rules is to provide them for distributed firewalls only. So we are going to change that behavior now. So we are going to say that it's not only applied to the distributed firewall, we are going to apply this to all edge devices. So that way we can be sure that the rule set is also applied on all the edges, so we could actually be sure that the traffic is going to work from that perspective as well. Click OK, click Publish Changes, and we should be good to go so that our firewall will actually let our traffic bypass so that we can access our web service again. Okay, so this is one scenario which would apply the traffic to every individual web server edge appliance. We can also do this differently to not pick all the edge devices. You could also individually pick one like our north and south edge device. And then again, we can click on the specific web page and we can see that the web page is still reachable. Both web servers on 11 and 12 are still reachable. How does this actually change the configuration of our edge device? When we go back into our north and south edge services gateway again, we can actually see that the traffic rule is now set up here as a pre-rule. So rule number 1 is actually what came from the system. In our next video, we are going to cover the NSX distributed firewall. In the next few minutes, we are going to talk about the NSX distributed firewall. In this video, we are going to take a closer look at how to deploy the distributed firewalls and how to create rules for the NSX distributed firewalls. This is going to be a live demonstration. In this demo scenario, we are going to move from the Edge Services Gateway Firewall to the distributed firewall. In this scenario, we are going to establish a firewall between the logical switches and the virtual machine NIC. This means we don't actually only filter traffic bypassing a router or an Edge Services Gateway. We are going to bypass every traffic with the firewall services, which gives us much more flexibility and allows us for microsegmentation without having to create a lot of individual network segments. For this scenario, we are going to create firewalls at the lower right corner just between the logical switch and the virtual machine. The rule set is going to be similar to what we did before. We are first going to establish a zero trust model, which means everything which is not manually allowed will be automatically blocked. So for that, we are going to create a rule which is going to allow access to both the web servers via HTTP and HTTPS. Once that rule is established, similar as before, traffic can bypass to the web servers. However, in that scenario, as we haven't allowed any communication between the web servers, app server and DB server, that communication would no longer be possible because now the firewall is actually blocking traffic off directly at the VM, so we don't need to first have to hit an edge or something else. So this firewalling methodology is allowing us for much more fine-grained traffic filtering and actually filtering traffic without having to build complex routing scenarios. Before we start configuring the distributed firewall, let's quickly check if our web servers are reachable. So web server 02 seems to be reachable and 01 as well. Go to the networking and security feature, firewalling segment, and over here we can actually define new rules. This is a bit like what we have done before on the NSX Edge device. You are going to create a section. In our case, we are going to allow one for web traffic. And similar to what we did with the edges before, we are now going to create a rule set within the distributed firewall segment here. So you can see you have basically within NSX only one area where you can define all the firewall rules for your environment, and this is exactly what we are going to do. So we are going to pick web server 01 and 02, move them over, specify HTTP, HTTPS service. So this is pretty similar to what we did before. And now this rule is on allow, but the default rule should actually be switched to deny, which was in the basic configuration we did before. We created all rules to be allow all for the beginning. So we can see now that the web service should still be reachable. So the default rule is actually removed and the new rule is in place. As a quick cross-check, instead of allowing the traffic, we are going to now actively rejecting traffic. Save this, publish the changes, and so when we run the rule set now, or when we run the access to the firewalls through the firewall for the web server now, everything is good. So again, from reject, we are going to reset this to allow. So now the rule is actually active again. You could also actually imply this not only on distributed firewall, on edges, or on both. So this is basically completely up to you. So you can specify where this specific rule should be applied. And once we change that again, we should now actually be able to access our two web servers again perfectly fine. Beside the layer 3 firewall, you could also specify a layer 2 firewall on the Ethernet level, same rules as with the layer 3 firewall. And you can also see that the system automatically saves configurations for every time you publish changes, and you could actually tell the system now that you were to actually remove or revoke the configuration of a previous time. So you could actually import it, export the configuration, or you can actually specify that you want to make a configuration change. Edit configuration is a bit misleading. It's not really the configuration you are editing, but the type of it. If you were to install like a Palo Alto firewall, they would show up under the partner security services, and you could use the same feature here. So overall, the primary hat about this is when you are using NSX with firewalls, you could have seen that there is not a big difference between edges and distributed firewall features. Both of them can use the same rule set, and then within the rule you can specify where they should be applied. In our next video, we are going to cover the service composer. In the next few minutes, we are going to take a closer look on how to use the service composer in a real-life scenario. In this video, we are going to take a look at how to create a security group and then how to apply security profiles with the service composer. Before we get started using the Service Composer, we are going to check that all our web servers are up and running. This is a best practice I always do when I do firewalling, no matter whether it's NSX or a different platform. Have a clear starting point where you know exactly what the current situation is before you make any changes. So currently our situation is we can access everything. So what we are going to create now is two security groups. One is going to contain all virtual machines containing the CentOS operating system. You could also manually include or exclude machines. And the secondary security group we are going to create is a security group which contains all the web servers. In our scenario, that's straightforward because all web servers are named web, but you could also use security tags or other parameters to specify which system you want to go and look for. Again, nothing to manually include or exclude. And then finally, you will see that we have two security groups, one with 8 machines, that's all Linux machines, and one with 2 for all the web servers. Next, we are going to create a security profile. The security profile basically can contain not only firewall rules, but also guest introspection rules, like which antivirus system should be applied, how should it be applied, etc. We are going to concentrate on firewalling rules because that is what every customer has. Guest introspection basically comes to life when you use additional tools. For the firewall rules, you are going to create a new firewall rule. For that, we are going to give it a name. Again, be as descriptive as possible. Remember, firewall rules might be something someone looks at 10 years ago. We specify that wherever the traffic comes from, and the target is going to be the policy security group, which means every security group we apply this policy to is going to be attached. And then we are going to pick the services we are going to allow. In our case, again, HTTP, HTTPS. Click the OK button. You could also disable the rule set and specify whether it should be locked or not. If you have a next generation firewall or intrusion detection system, you could apply network introspection rules as well. And finally, you are about to complete the rule. This does not automatically apply the rules, so we need to actually go to that and do that in a secondary step. Click on the Actions menu, click Apply Policy, and then pick the security group we created before and apply the policy. We are also going to create a secondary policy. This secondary policy is going to cover all Linux or CentOS machines should get SSH access. So again, we are going to create the security policy. And this doesn't need to be a security policy per service. You could also have a generic CentOS security policy which says SSH is allowed and we also allow ping and a few other things. It really depends on what you are going to do with it. Again, specify the firewall rule, what you want to do, allow, block, reject, what is going to be the target, in our case the security group, and the source is going to be anything. And again, you could change the state of the rule and whether it should be logging or not. Services, straightforward. A lot of services are pre-built. You can also specify and build your own service if you need to at your own pace. Click OK and we have a firewall rule set up for this. So what we did now is we created two security groups for CentOS and for web servers, and we created two security policies. Those are one-to-one links in our scenario. In real life, they are in many cases many-to-many scenarios where you actually imply different scenarios. To get a quick overview, you can switch to the Canvas tab, which actually shows you the security groups and what's actually applied to them. So you could actually identify if there are security groups cascaded into each other. You can see which virtual machines are included into this security group, which security policy has been applied to it, if there is any specific firewall rule, guest introspection or network introspection. That actually works for each individual security group in your environment. You can select and take a look at all these individual services. However, this implies that you need to know exactly what you are looking for. What I would like to show you later is how you could actually check this from an individual machine perspective. But first, let's take a look how all of this is actually reflected in firewall rules. You can immediately see here that the NSX firewall rule now has Service Composer firewall rules. two of them, one for the SSH, one for the web traffic. Those sections are automatically created and maintained by NSX. For the moment, we need to make one final change. We need to actually block traffic if it's not hit by our service composer scenario. So we are going to block the traffic from that perspective. We are going to publish the changes and validate that we can access still our web service. And we will see that our web servers are both still reachable through the firewall security rule created with the service composer. Now let's have a look on how this can actually be monitored from a virtual machine perspective, which is actually the more interesting piece. You see already when we get to the virtual machine that we have two security group memberships here immediately visible to you. The more interesting piece is you can switch to the monitoring tab and then actually select the subtab service composer, which will actually give you all the information about guest introspection, firewall rules, and network introspection services about this machine. And this is really the beauty of NSX. It immediately tells you which rules are applied for this machine, where do these rules come from, and how are they managed in the infrastructure. So this really makes a huge difference in day-to-day operation. In the last few videos, we covered the NSX Edge firewall, which is a virtual machine deployed in your infrastructure, and the different ways on how you could build rule sets for an NSX Edge, which could be edge specific, or you could use generic rules, which could then actually be applied over the edge and the distributed firewall, where you can also tell the system to apply the rule set on all edge devices or a specific one. We further on covered the NSX distributed firewall, which runs as a module on each individual host and can also deploy automatic firewall rules into each individual machine. Or not into the machine, but between the distributed switch and the machine. It basically is a firewall sitting on the VM NIC of the virtual machine, not the VM kernel. Finally, we covered in the last few minutes the service composer. This is really where all of this comes together and really starts to make sense. Because the whole rule set definition which we did with Edge and distributed firewall is just an enabling feature. The real life and the real beauty of microsegmentation, etc., comes from using the service composer, as you have seen. You define rule sets which imply objects, and you also imply security groups for these objects. And then you apply a security profile which defines what can be done. What we have covered here is the basic feature set with standard firewall rules. However, if you have guest introspection like an antivirus or something like that, or a network introspection like a next generation firewall, for example, then those could be applied with the service composer as well. And you also saw that you can immediately see the rule sets and everything at each individual virtual machine, which is really a beauty of itself, because it makes troubleshooting, etc., so much easier. In our next section, we are going to talk about third-party options in combination with NSX.
Welcome to the third section of software-defined networking with NSX. In this section, we're going to discuss third-party options. In this section, we're going to take a look at some examples for NSX firewalling and the service composer integration with third-party vendors. The first video covers some examples for NSX firewalling. In this video, we're going to take a look at NSX Edge firewall use cases, NSX distributed firewall use cases, the combination of both, and a cool feature called data security. Let's start with NSX Edge firewall use cases. So they're mainly used to separate the physical and the virtual space from each other. Or another example would be add security horizon view desktops. So they are used to separate the server and the desktop space from each other. Let's start with the separation of physical and virtual. We have a physical space and a virtual space, and in each data center we find something, a physical router and or firewall, or a device which has both features. We have a physical space, so I don't know any infrastructure having 100% virtualized. So we have physical servers in our infrastructure. In the virtual space, we connect an ESG to the physical device and have a couple of DLRs running behind the ESG. So what happens if we use an ESG in this combination? Firstly, we have the virtualization context awareness, which allows us to add rules based on networks or different objects inside the vCenter server inventory, as we have seen in the previous slide. So we keep the whole traffic within the virtual space. So if two virtual machines need to talk to each other, we keep the whole traffic behind the ESGs, and that leads to a massive reduction of bandwidth usage on the physical device. We reduce the CPU load on the physical device, and we reduce the complexity in the rule set. Because behind the ESG, we use the virtualization context awareness and create rules based on that, and add kind of an automation to the infrastructure, and the physical device controls the traffic flow between the physical and the virtual space, and of course to the internet. Another example is Horizon View. So we have a physical router and or firewall, and behind that device we have two ESGs. One is responsible for the virtual servers, and the other one is responsible for the virtual desktops. So that leads to a couple of cool things. First, we keep the server traffic inside the server networks, and if there is some, we keep the desktop traffic inside the desktop networks. Plus, we use the two edges to control which traffic flows between these two network segments. So we add lots of security to these without adding bandwidth and CPU load to the physical device. NSX distributed firewall use cases. So we can add security within a single IP subnet, like servers or desktops, as we have seen in the previous slide. So we reduce the need for different networks for multi-tier applications. We discussed that during the microsegmentation. And of course, we're trying to automate the network and security together with the application to create an application-centric view within our infrastructure. Let's start with the security within an IP subnet example of the distributed firewall. The DLR has multiple networks behind, and the DFW is used to add security within a single IP subnet. That is pretty cool, and NSX is the only tool or the only application you have to do something like this, have a firewall within a single IP subnet. The next is the microsegmentation. We have a 3-tier application. In the past, you had a physical firewall box, 3 VLANs, and you need to make sure that the traffic goes to the firewall and be inspected by the firewall. So in our case, we just place an NSX edge in front of the application, and that NSX edge allows incoming traffic to the web server. And the DFW is responsible for allowing web to application server traffic, and of course allowing traffic flowing from the app to the DB tier. So that is something microsegmentation which is really cool within NSX and reduces the need of lots of networks to have per application. And that leads directly to automation. So we have our 3-tier application, web app and DB, plus DFW doing the security within this application. So we use the service composer with security groups and policies, and that helps us automate the deployment of complete applications. How is this done? So from my perspective, you just grab this application and it is kind of transformed into something we call an application pod, or I call it an application pod. And this pod is just a single object. So the user who connects to the self-service portal gets this application pod published. So I entitle the user, allowing him to deploy that application many times. And that is the cool thing about microsegmentation plus automation using vRealize automation. Let's go to data security. Data security allows to look after very specific data within the virtual machine, like a credit card number or a social security number. So that is done using an ingest agent. Of course, we need something to scan for very specific data. And data security has pre-built compliance profiles, so like PCI DSS, for example, or HIPAA. So data security is a built-in feature or service of NSX. Let's do a short example. We have 2 security zones. We call them normal security zone and PCI DSS security zone. and each zone has a very specific policy. So if we have a virtual machine with the in-guest agent, and you store a file, let's say a text file with a credit card number in, so you store that file in the virtual machine, the in-guest agent detects that there is a file with a credit card number. So what happens next is the virtual machine is tagged. And because of the tag, the virtual machine is placed into a different security group. And based on that security group, it gets a different policy assigned. So it's now moved to the PCI DSS security zone. And this policy applies a different DFW rule set underneath the virtual machine. So if you delete the data within the virtual machine, it is moved back to the normal security zone. And that is how you can automate security plus data within your infrastructure. The next video will cover the Service Composer integration with third-party vendors. Welcome to this video talking about Service Composer integration with third-party vendors within software-defined networking with NSX. In this video, we're going to take a look at how to integrate third-party solutions into NSX. A short recap. The Service Composer allows to dynamically add firewall rules, guest introspection services, and network introspection services. This is done using a security policy and attaching the security policy to a security group. We have built-in guest introspection services called data security. They have pre-built profiles which can be applied like PCI DSS or HIPAA, and we use an in-guest agent looking for specific data like credit card numbers or social security numbers. The third-party guest introspection. These third-party solutions include antivirus, anti-malware, or vulnerability scanning. So they add lots of additional features to the whole infrastructure. The whole management, and that is the cool thing about the integration, the whole management is done within the NSX UI. So you just need to attach the solution to NSX and do the management using the NSX management UI via the vSphere web client. So that's the integration. You register the third-party solution within NSX Manager, and the NSX Manager deploys the virtual appliances on the host. And then you create rules to redirect the traffic for scanning, antivirus, anti-malware. So a couple of examples are McAfee, Trend, Rapid7, Symantec. So McAfee, Trend, they have antivirus solution, Symantec as well, plus anti-malware. And Rapid7, it's a pretty cool anti-vulnerability scanning. That is a solution like it tries to detect is a very specific patch installed into the guest OS, yes or no, and if not, the virtual machine is tagged and therefore moved to a different security group and gets the patch installed. If everything's fine, it's moved back to the original security zone. These are just a couple of examples. So third-party network introspection, they add advanced firewalling services to the solution like layer 7, or it is configured by the Service Composer. So you create a security group, a security policy, and then you add a traffic redirection rule to the security policy. So how is the integration done? It's pretty similar as we have seen in the previous example. You register the third-party solution within NSX, and you use the NSX Manager to deploy the virtual appliances to scan the whole traffic. And then if you add a virtual machine with a security policy, the security policy says, redirect very specific traffic to the virtual appliance for scanning. So it might be a web server and you redirect the HTTP, HTTPS traffic to the PAN. The cool thing about these third-party solutions is because the virtual appliance is deployed to every ESXi. So if you move the virtual machine using vMotion, there is another appliance which has the exact same configuration and the traffic or the scanning of the redirected traffic is not interrupted. So the whole solution, the same for advanced firewalling and antivirus solution, the whole thing is vMotion aware and is compatible with the whole vSphere feature set. So let's do a couple of registration examples to see that it's pretty simple. So in Trend Micro Deep Security, you go to the web UI and just add a vCenter server, and then it is registered. Add the credentials, off you go. Another example is Palo Alto. Just add the Panorama web configuration page, go to VMware Service Manager and add all the stuff you need to register Palo with NSX. The summary. So we covered in the previous video some examples for NSX firewalling, distributed and edge and the combination of both. And in the last video we covered the service composer integration with third-party vendors.